All right, I think we're live or something. Hey guys, welcome to the third episode of Ferris Makes Emulators. I'm Jake, or Ferris, or whatever you want to call me, and today we're going to still be working on our N64 emulator. So a couple quick things before we just dive right into it. Hopefully you've watched the last couple episodes of this. If not, I will grab a link for that right now, so let me just do that really quick. While I'm doing that, actually what I want to go over first is some, basically stuff from the last one. Last time we basically got to the point where, we have a CPU kind of working or something, and it executed a single instruction from the boot ROM of the N64, which is pretty rad. Today we'll be continuing with that stuff, but I got a couple like pull requests and things in the meantime. And I kind of want to go over that stuff. Almost got that link here. And yeah. Here we are. Here's this link. Oh, whoops. That's what happens when you mash all the wrong keys. There we go. There's the video playlist. And this video, of course, will be a part of that as well when we're done. In the chat, XSKE, Ferris, you inspired me to make a NES emulator in Rust. Already got code executing, although not all instructions yet. Awesome, really great job. That's really cool to hear. Really cool stuff. Actually, if you could paste a link to that, I'd be happy to share that. Yeah, so let's just get into this. So, as I said, we got a couple like pull requests and stuff, which is really cool. Actually, the first one I want to go over is I created an issue because I really wanted to decide on a license. And I wanted to do this early on so that I could start, getting contributions in properly and all that kind of thing. I was originally thinking BSD2 because that's usually what I go for. But after some discussion with a couple of people, we realized doing dual MIT and Apache 2 is going to be our best option, mainly to conform with a lot of the other Rust ecosystem and also to provide the kind of freedoms and protection that I wanted to provide for the project. So we're going to go ahead and do that. Walk 2 MIT license for the win. XSKE. It's not on GitHub yet, but I could pop it on there real quick. Yep, if you do that, give me a link. I'll share it on the stream. That'll be cool. So as for actually licensing the whole thing and then getting all the files in there, we had a contributor who gave me a pull request for this. BB2000 added this. So we looked over, looks good. So just gonna merge this on the stream here. Because the whole thing is that I don't want to write any code on the stream, and kind of accepting pull requests kind of feels like that as well. So we can go over this in detail, but it's really just we added to the cargo.toml file, which is our Rust project file, the fact that it is actually licensed like this. We added the Apache license file and the MIT license file as well, and also added some information in the README about the licensing, and also a little note on contribution, which is basically, unless you explicitly state otherwise, contributions are going to be submitted as defined by these licenses. So I'm just going to merge that really quick. Go here and merge. Bloop. Fantastic. Ashmedai, I think most of us in here are now toying around with writing emulators in Rust or similar projects. Awesome. That's pretty cool. Or planning on doing it. Failzow, hey Ferris. Hey Failzow, I think you say that. Failzow. XSKE, he got his emulator here. I'm going to pull that up. So I guess it's XSKE/NESEMU. Cool stuff. I do kind of want to poke around here a little bit. Cool, I like how you modeled the flags like this. Bunch of little bools there. Instead of actually packing it, and then you can pack it and unpack it when you actually address those. Because 6502 does have instructions to read the PSW. At least it has instructions to push that, I believe. Push and pop it. PLP and PHP, I think. Because push and pull in 6502 lingo. Walk 2, I started writing a NES emulator due to your series, though coding it in C because star me. Yeah, but that's cool. I love hearing about that stuff. That's awesome. So cool. So go ahead and check that emulator out. I'll probably go dig through that a little more later. But I do want to get back to the one that we're working on here. So cool. So we merged that pull request, and that should fix the licensing issue. So now this project is licensed under dual MIT and Apache 2. And the reason why I think that's really important to get done early is because, like, I actually have a policy where I won't clone or contribute to any repos that don't actually have a license. And that's because my understanding of, copyright and all this other thing is that you're actually not technically allowed to do that, to actually take this expression that someone has made and modify it and do all that stuff without having that been stated by a license, even if it's open source in a public repo on GitHub. My understanding of that is just that oh yeah, you can go read the code and everything, but you can't actually make changes to it. So I want to get the license stuff in here early, because I'm sure there are other guys like me who also feel that same way about this. So cool. So that's done. Another thing is, let me read the chat a little bit. That's weird. Just got a notification about a merge pull request a split second after I saw you do it. That's pretty cool. Thanks for watching the repo. Probably due to the 20-30 second delay of the stream. Yeah, there is some stream delay. XSKE might also want to look at the bit flags macro. I would also recommend that. Yeah, excuse me. I'm still draining from being sick, so I'll probably snort and cough and all that other gross stuff. Yeah, so there's another issue about ediness related operations in the standard library. And really quick what that's talking about, let me pull up the code, is we were mucking around trying to get instructions to execute last time. And I believe it was here in the interconnect. We were going to read a whole word from memory or whatever else. And here I just went ahead and I just did all this bit shifting myself. Just because I know how to do that, and it was faster for me to do that than learn how to use different methods in the this crate called I believe it's byte order. Yeah, byte order crate, which actually can do this for us, and we'll be switching to using that in this one. But yeah, so I just ran ahead and did this sort of on my own. We got another quick pull request about that first, which is that there was a bunch of alignment stuff that wasn't quite savory there, so someone just went ahead and fixed that. So I'll merge that really quick. So that was Discoloda, I believe, is watching now. So thank you for that. Pretty cool stuff. So yeah, so we'll merge that. I'm going to do a pull locally. What? Oh, yeah. Updated all my Xcode stuff, so we got to do some sudo stuff. I've not agreed to Xcode license agreements. You must agree to both license agreements, whatever. Yep. I have agreed to this before, and I'm going to agree to it now. I'm reading this really quickly, I promise. Thank you. Agree. All of a sudden my git config seems to be a bit strange, probably because I ran that as sudo. Oh, also because I'm totally not in the right repo. There, that would help. Dev projects cd rustendo. Yeah, we'll get pull in there. Cool stuff. Good. Now we have all that locally. Reload this file. Now I got this beautiful alignment stuff. Like I said, we're going to be replacing this with byte order in a sec, but it's still cool to get that contribution. So thanks again. Yeah, so that was 2 out of the 3 pull requests. This third one was a discussion about still using default for initializing default fields. Again, when we were going through the code, I believe it was in the CPU in particular, we were using default to initialize all these values because a lot of these just go to default values like 0 or false for the different data types here. And we ended up not doing that because we used dependency injection to give this interconnect here to the CPU. So this was about using default to try and initialize all this stuff, but still also supporting this. I decided that I didn't actually want to do that because you could end up with a case where someone initialized this struct using the default mechanism, and then this interconnect field wouldn't have been set properly. Whereas here, if we take this as an argument to the new function here, the only way to make an instance of this CPU struct is to give it a valid interconnect. And I like sort of enforcing those kind of things. So we're going to go with that. I believe Kryzy was the user who was talking about this, and I think he was going to look at another way of doing this. I don't know if he actually did, but I kept it open for that because I thought the discussion was pretty interesting. Emoon, who is Daniel Collin in the chat, also I think he mentioned another cool trick, which wasn't exactly the thing we needed for that, but it was still, I think this was a way to nicely abstract platform-specific things, or in particular platform-specific implementations of different, library features. So that's pretty cool. So I think that's all of the open issues and pull requests. The last one is this endiness related thing. And I'm actually just going to go ahead and close that now because, or actually I'll close that when we do the commit, when we actually bring in byte order on this. So that'll be cool. So I think that's, Move Away says, missed the very beginning of the stream. Are you going to be capturing chat somehow for the recording? So actually, I did some thinking about that. Because at the end of the last one, I said that I was going to try and record the chat. But basically, what I kind of concluded is that it might end up actually becoming a liability if someone posts something that I'm not able to broadcast, or I shouldn't broadcast, even if it's just a link. I kind of feel like that, like I'm liable for that when I'm putting this content up on like YouTube later. So I think the VODs on Twitch actually get recorded. I think they record the chat, so I think we'll get it there. Other than that, I think I'm just going to have to keep reading it, as far as I know. Someone please correct me if I'm wrong, though, because I would love to be able to record the chat, but I think I'm kind of saving my ass by not doing that. XSKE, there's always rechat. I would love to know what that is. Also, my overlay is sexy AF. Thank you very much. The extra care for defaults and whatnot was so that we could avoid the vex, right? We had to use them for box. Yeah, that was another reason we did that. Yeah. XSKE says Twitch VODs do not record chat. Sorry about that. There's a third-party Chrome extension that does record it, which is rechat again. It only saves it for 7 days, though. But it plays the chat alongside the stream in the chat box. So that's pretty cool. Again, I still kind of think the content in the chat might become a liability. I don't think we've had any issues with that yet, to be fair, but you never know. So. Ashmedai says, just briefly recapture what was said if you address something on chat. Rewatch episode 1 and 2 on YouTube. You missed some context as a viewer when you respond to the chat. Yeah, that's kind of unfortunate. So I'm gonna try to do my best to at least be reading the things that I'm responding to. Beyond that, I don't think there's much I can do about that. Ion1, first time I can follow this live. Yay! Thanks for joining us. I think it's a lot cooler to have this live experience as well. Yeah. So let's go ahead and do this byte order stuff now. I don't think we have anything else to do. Let me check my notes, actually. Oh, I do actually have a couple more notes. So one of the things that at least I struggled with when we were doing the stream last time is there's a lot of information about like how MIPS does memory mapping, and I wasn't sure if like that was N64 specific, and so we kind of read through a lot of documentation to find out these very basic details. And I found a ton of sources online that go over like in way better detail in much clearer terms than that data sheet that we were reading. So I do kind of want to go over some of those things that I find because it was pretty funny. TJS guys, let the man stream. Thanks, man. Yeah, so the first resource I want to go over is a book called CMIPS Run. Now, CMIPS Run was recommended to me by a couple people, both on and off the stream. And I did take a look at that through the Google Books preview, and it's really good, guys. Like, if you're interested in MIPS, I highly recommend that book. Unfortunately, because like I was able to find the PDF on some like sketchy Chinese websites, and I'm not really sure, how the copyright situation is there, and so I don't think it's actually something that's meant to be publicly available. So I won't be broadcasting it, and we won't be reading it on the stream. But I would recommend going through that, especially for the stuff on like how MIPS boots up, how the memory mapping works. It is very, very clearly explained in that book. So that was really cool. I think, again, we're past the point where we really need that right now, but for those that are curious, I wanted to point that out. So some other things is that I found, and I can link these in the chat as well. I'll probably link them here. But these are just like Google searches, and it's stuff like these people would post their, like this guy gave a MIPS introduction talk. And I think it's like the 5th or 6th slide we have here, register organization, and here's all the names of the different registers. So this is something we fought with towards the end of the video. We had a register called T9, I believe, and or was it T1, or was it, yeah, T1 here. And the index of that register was register 9 in the general purpose registers, and I was really confused at why that was. It was just because T is like arbitrary names for registers 8 through 15. And we found a table like this later as we searched for it, but yeah, this is like one of the first things I think I found when I searched like MIPS registers, like the second or third hit on Google. So that's pretty fun. So I'll go ahead and paste that in the chat. Another thing that I ended up finding here was another thing I found, like going over MIPS boot process, I think is something I Googled. And here, like, scroll down like a page and a half, and you have the memory model and the memory mapping unit. And here we have this exact table that TJS guided us to last time in the data sheet that goes over these different segments in memory for how the MIPS processor views the memory. So there's this user segment, which has these, cacheable and TLB mapped stuff. And then there's this kseg1, which is the one that we're going through. No, it's actually kseg1 that we're going through when we actually look at the boot ROM, that kind of stuff. It's just the reason I bring all this up is it's just kind of funny, like, to see how easily or how easy it is to actually find this information once we kind of know what we're looking for. So it's pretty funny. Ashmedai says, "Dang, there's a first edition from 1999." He's talking about CMIPS Run. Now he sees there's a second edition from 2006. I believe I also found information on the 2010 version, which was called CMIPS Run Linux, which is about actually getting Linux kernels to boot on there. That looked pretty cool. Yeah, and again, you scroll down a little farther, here's all this register information. So it's like all the stuff we needed, and it's like right here. It's kind of funny. So I'll paste that in the chat as well. Bloop. And I believe I found, oh yeah, this was another one. So I think it was Creelers is the guy's name on Twitter, sent me this. This was a book on emulation. I'll paste this in the chat right now. Book/paper on emulation, a study of the techniques for emulation programming by a bored and boring guy. The author, Victor Moya del Barrio, Computer Science Engineering, FIB UPC, 18th of June 2001. And this document goes over actually quite a lot of things in emulation. So if you guys that are writing your own emulators, I would recommend checking this out. I found this a few years ago, but it was awesome that he brought this up and showed this to me again. Especially different things about like CPU emulation core, doing interpreter or binary translation. We'll be doing continuing working on our interpreter, which is the method that we've chosen so far to do our CPU. But I would actually love to do binary translation later, so we'll probably do that. Different things about memory emulation, GPU and emulated devices, communication, interrupts, and timing. Really good stuff. And again, I have read through this a couple years ago, but I definitely need a refresher, so I'll be reading this again. Really good stuff in here. Pretty long book. Did I? Yeah, I did paste that. Awesome. And I think, yeah, this was the last thing that I wanted to go over. Mike Ryan on GitHub, he sent me an email and told me about this N64 dev repo. which I also found previously in Start, but that it was cool to get the refresher. So this actually includes a ton of stuff, like different documents and libraries and different kind of source code. It's all related to actually developing stuff for the N64. In particular the docs folder in here has a lot of really good stuff and stuff that we're probably going to end up digging into later in the stream. Just basically about how the system works, just documentation on the system, which is of course going to be invaluable for us as an emulator or as emulator authors. So that'll be really cool. So that's I'll go ahead and link that in the chat as well. And I think that's everything from my notes. Almost. A couple more. Another thing is that we were talking about when we were doing the endianness stuff. Again, back to go back to interconnect. We were talking about endianness here. So here, like when we're reading these bytes and loading each one of them individually into a number, it matters which order we're reading these and how far we shifted into the number. But in terms of actually like endianness, once we've got the number internally in our CPU, then it actually, we don't really have to care about endianness. We can just think of the whole number as like a big endian string of bits. And that matters later when we go back into CPU where it's starting to do all this decoding stuff. At this point, we don't have to worry about endianness. And I think I actually said something wrong about that last time. That's why I'm bringing this up. I think I said that, oh, I can assume that this is like a little endian, whatever, but it's actually like not the case. We assume this is a big endian string of bits, and it's only when we're actually loading from a stream of bytes into there that that's going to matter, or if we're going to like reinterpret a pointer. So if we have like a byte pointer and we interpret it as an int pointer, then the endianness of our host CPU is going to really matter a lot, because you can basically think of it like internally in the CPU, we're always working with, as I said, a big endian string of bits. But then when that CPU goes to read and write words and read and write integers, things that are bigger than a byte, it has its own like serializer, you could say, which is defined by the endianness of the CPU, and that will either read or write in bigger little endian. And if we never actually touch that memory directly, except going through this CPU serializer, we don't have to worry about it, and so that's not going to be something we have to worry about. The only place we have to worry about it is right here, which is where we're actually reading from a string of bytes manually into a value, which is U32. And then because we've done this order explicitly, because we know that that's going to be big endian, we don't have to worry about anything else. And again, when we use the byte order crate, we'll basically write the same thing but smaller, because it has this stuff internally. So we don't have to worry about making mistakes here. So I wanted to talk about that. What was the other thing? Yeah, I think, yeah, that was everything. So that's cool. So now let's get into actually using this byte order crate. So a couple things about this. What we're trying to do here semantically is we're trying to load a U32 from a byte stream, from a byte stream where, how do I word this? The point is that we have there, we'll do this right like this. We're loading a big endian U32 from the byte stream, and so as you can see with like, because I read the first byte and then I shift it left 24 bits, then the second right and I shift left 16. Like we get those in the correct bits. But what the cool thing is about this byte order crate, if I go on the documentation here, I'll link this really quick as well. If I go to the documentation down here, by the way, for those of you guys unfamiliar, crates.io, this cargo thing here, this is the Rust like basically package repository. It's awesome. And so I'm just looking at the byte order crate on that site. So you have like the home page of the crate and the repository, which I believe are the same thing in this case. Yeah, this GitHub repo. And then you also have a link to the documentation here, which is what we're looking at. In particular, if we look down here, it talks about it has a byte order trait, which is like Rust generics. Specifies byte conversion methods for each number type in Rust, minus numbers that have platform dependent size like usize and isize. And here's actually what we're interested in. Two types, big endian and little endian, implement these methods. So if we go ahead and look at big endian, which is down here in the enum section, it has right here this function called read_u32. And it takes a buffer, which is a reference to a slice of U8s, which is like a view of consecutive U8s, and then it will return a U32. So go ahead and click on that. Yeah, read_u32, reads an unsigned 32-bit integer from buff. Panics when buffer.length is not long enough. We're not too worried about that. So this is actually what we're going to use instead of doing all the bit shifting that we were doing. So what we need to do to pull in this crate is we go back to this page on here, and you can see it says cargo.toml here, which again is our package file. And we're going to go ahead and just copy this here, this byte order equals, and then the version here. That's what that is. So if we go back to, if we open our own cargo here, just in case anything gets, anything in my overlay gets in the way. So it has this dependency section. And all we're going to do is just add that line there. Go ahead and save that. And now when we go back here and we build this, so cargo build, as you can see, it's going to update its registry, which is like its internal understanding of that website. And then it went ahead and found byte order, it compiled it, and then it compiled our project. And of course, we get all these warnings that we've been getting just for stuff that we haven't been using yet. But cool, that's actually all we needed to do to get the byte order crate. So now we're going to go ahead and use that. BB2000, are you using the new version of Rust 1.6? I believe I'm actually on the nightly from before. So if I run rustc version, I'm on 1.6 nightly, so I guess I'm on a couple versions back. So I am using 1.6, but not the official release one. I'm using nightly. It's not gonna make much difference for us right now. But yeah, so now we actually want to use this method. And where was this? Yeah. So yeah. So let's go ahead and we open our main file. And here we want to extern crate, is it called byte order in all lowercase? I believe it is, yeah. Byte order, and that will actually pull in the crate so that we can use it. The next thing we want to do is we actually want to import that later. So if we go into source CPU, we use interconnect. I also want to use super byte order. Where was that? Yeah, we'll just pull in big endian. So then we should be able to say down here, whoops, I did this in CPU, that's wrong. I meant to do that in interconnect. Let's go ahead and put that up here. And then when we go down and actually read these bytes, instead of doing this code here, we'll go ahead and do big endian, and we'll probably have to also bring in this byte order trait, but we'll get there in a second. So big endian, read u32, and then this expects this view of bytes here, and I believe actually JuggleTux on GitHub actually gave us exactly the code we need here. So what we actually do is we take a reference to our PIFROM here, and then when you create a slice in Rust, which is again a view of like consecutive data, if I just put ... here, then that would give a slice that points exactly to our PIFROM, the whole thing, but we actually want that to start at a specific index. We want it to start at relative address. I believe that's correct. And then we cast that as usize, of course. So again, what this is doing is just giving us a view of the PIFROM starting at this relative address. And then we'll give that into this U32, and don't need the semicolon there, and that should do it. So if we go ahead and run this, Yeah, and this is saying what I was saying. So no associated item name read32 found for the type byte order big Indian, because when you use traits on types, you need to also pull in the trait. So we need to pull in byte order, byte order. So that's pretty easy to fix. We go back up here, and not only do we want to use big Indian from here, we also want to use byte order. I should do. GNU Vince, hello to you. Thanks for joining us. So yeah, built cargo run. Yeah, of course we need to specify the command line arguments. ROMs and 64 PIF data was our data. I think the order of the arguments that I had was first the PIF ROM and then the ROM file. So that's cool. I believe we were using the fire demo here. Cool, so it looks like that ran. And if we remember from last time, we were just printing the states after every instruction, the entire CPU state. So it's a bit verbose right now, but yeah, so we print the initial state. As you can see, all these like registers have default values. Then we got LUI. And then, don't remember what this RT thing was. But then we print the state after, and you can see this register here changed. So awesome. Zagjev, have you tried using cargo mode? It lets you build from within Emacs. I haven't, but maybe I'll check that out later. For this stream, I'll continue to use the command line. GNU Vince, is there no lower quality stream option like 480p? My connection seems to be unable to handle current HD quality. I'm only streaming in HD. I thought Twitch might be able to convert on the fly. I guess not. So unfortunately, there may not have that option. But yeah, so this looks like it worked. So what I want to do is go ahead and remove this other code. And so we don't need to check the NES or check out the byte order crate. Cool. Yeah, so now I'm just going to go ahead and commit this. Make sure that was everything we did. Yeah, because we're committing our lock file. That's why that comes up. Good. Yeah, so pulled in byte order and fixed, I'll say interconnect. I'll say fix any issues. Because I don't think we'll have any issues other than just actually reading these streams. And then I'm going to fix this. This is number 6. Fixes number 6. Go ahead and commit that, and I'll push that. And there we go. So that issue is closed. Great. Awesome stuff. So now our next step is I wanted to continue. So we actually are at the point now where we're actually running instructions. And I'm actually okay with just continuing to print this whole state here. I know it's like really verbose and stuff, but it'll be fine for us to just scroll through this every time. First of all, I want to define what this RT thing was. I don't remember what that was. It's probably in CPU. Oh yeah, that was the target register, because we were worried about the decoding there. So I'm going to go ahead and remove the printing stuff from LUI here, because what we're actually going to be doing is we're actually going to be implementing the other instructions in this boot ROM, so that'll be pretty cool. A couple of the guys on the stream are talking about just listening to the stream if they can't get the proper video. I hope that works. I am going to try to talk through and explain what I'm doing. And you can view the code on GitHub, so maybe that works. Maybe that's a good option. Probably not the best. But yeah, so our next step here is actually to just like continue running this until we start finding instructions that we don't actually recognize. So what I actually want to do is we have the state before and after here. What instead I want to do is remove after here and make this a little loop here. And I want to, actually this is the whole N64 state. Go ahead and print that and then run an instruction. I just want to do this in a loop now. So now if we run this, it printed our state. Here, let me clear every time I build as well. So now every time we run this, we should get, yeah, the state of the CPU printed, and then it'll run the instruction, and then the next state of the CPU, and then it'll panic as soon as it finds an unrecognized instruction. So that'll be okay. Walk 2, you can guess what he types with the keyboard's clickiness, like hard code or like hard mode. Good luck with that. Yeah, that the reason why this is panicking again is because we found an unrecognized instruction. So what we're going to do is start actually filling these out. So if we look at this unrecognized instruction, we actually have what instruction was here. We could look at that, or we can look at our online disassembled version of the PIF-ROM, which again we had last time. And all we did again to find this is that we had, I just opened the thing up, this PIF-ROM in HexFiend, which is this little hex editor, and I just copied and pasted that into this online disassembler, and I made sure that the architecture was MIPS 4300 and that the endianness was big, so I can actually decode this properly. So what these 4 bytes are, if we look at these, they should match. I guess that's probably covered by my face. Yeah, but it's these 4 bytes here, 40, 89, 60, 00. 40, yeah, and as you can see, that's this second instruction here, which is what we expect. So that's supposed to decode to MTC0, T1, and 12. So what I'm guessing this will do is, so this first instruction, this LUI, loaded this value into T1, which is one of our registers. And I'm guessing that MTC0, if I remember correctly from what we found out in the previous streams, is that we're going to transfer a value into one of the coprocessor registers. So I believe this is going to take register T1, the value in that register, and put it into controller or coprocessor 0's register 12, and we'll find out what that is. XSKE says ODA doesn't support 6502. That's unfortunate. I'm sure that there are different tools as well, though, that you can find for 6502. It's not like that was not a popular processor. If you find any, actually chat and you let me know, then I can talk about those. I like 6502. So yeah, so we're going to be looking at MTC0. So what we need to pull up from my documentation is our user's manual again. So let me go ahead and find that. Yeah. Go, I'll close that. Awesome N64 picture. And I also want to view the table of contents. It's going to help us a lot when navigating. Let me pull this up. Zoom bigger. Yeah, so again, that instruction was MTC0. So let's actually just search in here for MTC0, because I believe, yeah, here we go, the system coprocessor instructions. So this is, yeah, MTC0, move to system control coprocessor. Loads the contents of the word of the general purpose register RT of the CPU to the general purpose RD of CP0, which is the coprocessor. And I believe we will find later, oh, there's a double word move, that's cool. Because I wanted to find down here where it actually had these nicer representations of these instructions. So hopefully they just have one for MTC0. It looked like it had MTCZ, if I read that correctly as it zoomed by. Yeah, and this should be basically the same thing because I think it's saying move to coprocessor Z, so we could have multiple coprocessors. In the case of the N64, I think we only have two, or maybe three. Can't remember. But yeah, so if we look at MTCZ, this should be what we're looking at. Yeah, so this is our instruction here, MTCZ, and let's go ahead and move that so we can work around it. Hopefully none of my overlays are covering that up. Good, we're looking good. Yeah, so what I really like about this representation is it shows us the exact encoding here with all the various different bits and what they're going to be like. So this is a really nice view for this. It also shows us the format, so if we're going to write this in assembler, we have the target and the RD. I'm not entirely sure what RD was. RS, I guess, was source. RD might be, yeah, again, not really sure. But as we can see, we have the 6 bits that define the actual instruction. And as you can see, it's this 0100 prefix. Then it has XX star. It does say refer to the table opcode bit encoding on the next page, or 16.7 CPU instruction opcode bit encoding. I'm guessing that what that will do is just 2 bits to encode which coprocessor is. Which I believe the system supports up to 4 coprocessors, which would then make sense if there's only 2 bits to encode that. Then we have MT. I'm not really sure what that was. Oh yeah, okay. So this I guess defines that it's going to be an instruction related to a coprocessor. This defines the actual instruction then, in terms of the coprocessor instructions. This is going to be the register we're going to read from. This is going to be the maybe it's destination is what RD stands for, but this is the 5 bits encoding which coprocessor register this will actually go into, and then we just have 11 bits of nothing. So pretty simple. BAFTAC, are you going to put the instructions into struct enum, or will you just leave it as is for now? I don't think it makes much sense to put it in a struct or enum unless we can get automatic decoding of it. Because if we're going to put them in a struct and enum, we have to decode the instructions to put them in the struct or enum. And then, it might make our match look nicer in this piece of code. But again, we still have to do something that looks like this, as far as I know, to actually get them into those structs to be able to match on them. So I'm going to leave them as is. Going to make the whole thing simpler. BB2000, to do MTC0, CP0 needs to be properly implemented. Yes, I am aware that because we will then be, as soon as we call this instruction, we'll be interacting with CP0. So at least certain parts of it are going to have to be implemented. So that will sort of start to lead us down that rabbit hole. But I think that that's just what we have to do. Birkenfeld, how about a new type around U32 for instructions so you can put helper methods like opcode on? You could also implement debug on it to get assembly-like representation. That's not a bad idea. I'll consider doing that. Also, the page above has MTC0, says BB2000. If you look up here, oops, suddenly my scroll bars being a bit, or my scroll wheels being a bit strange. That's annoying. Yeah, it is right here. Yeah, so it looks actually, if we look at the encoding, it looks actually to be exactly the same. When I looked at this, 0100 with XX. Yeah, it looks like it's exactly the same stuff. Which is cool. Man, why is my scroll wheel not going up there now? I'm able to scroll down fine, but not up. That's annoying. But yeah, let's just go ahead and use the MTC01 as a reference here. But I do think the only difference that I saw between those was these bits. Maybe there are some operational differences here. But yeah, we'll use this one. XSKE, if you look at my opcodes.rs and my emu, I had a giant lookup table filled with structs. You could probably adapt that to MIPS instructions. Yeah, we might have a look at that later. I think right now I'll just continue with the current strategy, but I'll definitely have a look at that. Walk 2, the thing I was stuck with my emulator is testing the CPU emulators correct. I found a bunch of NES ROMs that are basically test suites for the emulator. Is there anything like that for the N64? I believe there are a bunch of test ROMs like that for the N64. The problem is to get any code executing on the N64 at all, you have to be able to have executed the PIF ROM already to be able to actually load any other custom code on there. So even if we did find those, which we probably will later, we still have to get through the code in this PIF ROM to be able to run any of that. So we'll look into that when the time comes. Yeah, so let's go ahead and look at MTC0. So we match the opcode here for LUI. We're going to go ahead and match on this new pattern. And I'll just hard code that here, even though the other MTCZ instructions were similar. MTC0. So let's go ahead and decode the different pieces. Now I believe if we look at RT here, this was instruction shift right 16, and then this bit mask here. I believe it's in the exact same spot here as well already. So we can go ahead and reuse RT. And I'm guessing there's going to be a lot of cases like that. Oh yeah, here was another thing that I want to go over really quick. I wrote a note here to do check 32-bit versus 64-bit mode for sign extend on this instruction. Currently 32-bit mode is assumed. I did some talking with TJS off the stream. We were talking about sort of how this 32 and 64-bit modes work in this CPU, and it actually seems to be really strange. Like all of the registers are internally just kind of seem to operate on 64-bit values anyway, so we could just kind of assume that this sign extend would happen. And there is like a bit flag somewhere where you can actually set which mode the CPU is in, either 32-bit or 64-bit. But the thing is that that bit flag itself is actually undefined when the processor starts up. But the address of the boot ROM is always going to be the same in 32 or 64-bit. I could pull up those tables again, but I don't think it's that necessary. But basically, in either mode that the processor is in when it starts up, it will always go to that same boot ROM address. It will always execute the same boot ROM. And in 95% or so of the cases for the CPU, it doesn't actually matter what mode the CPU is in. And I guess we'll see with the PIF ROM that it's not going to be something we have to worry about. So I'm gonna leave this note in here for me later because I didn't do the sign extend here. So I'm gonna leave that note. Actually, write this to do sign extend for upper 32 bits. And then if we just add that later, then we can call that instruction done. Yeah. So so now we'll go ahead and look at MTC0. Sorry, I'm a bit scatterbrained today. A lot of stuff going on. So we had, yeah, not only do we need to decode this part, but we also need to decode this MT part, I understand. Because if we looked at the encoding on MTCZ, we saw that these bits encoded the coprocessor. And if those were 00, which is probably the case, we might end up branching on that. Actually, I think we'll handle that case when we come to it, because for now, this is the only one we're going to hit. Yeah, let's just leave that as is. So yeah, so we need RD, which is going to be instruction shift right 11 bits, and we'll take 5 bits of that. And then, yeah, the contents of general purpose register RT are loaded into the general purpose register RD of CPU0. Because the contents of the TLB may be altered by this instruction, the operation of load instruction, store instruction, and TLB operations immediately prior to and after this instruction are undefined. And that probably makes sense. If the register manipulated by this instruction is used by an instruction before or after this instruction, place that instruction at an appropriate position by referring to coprocessor 0 hazards. So it's probably just telling us that, like, it's not necessarily defined when the coprocessor write or read will actually take place in relation to the instructions that we're reading and writing. So it might like happen on 1 or 2 cycles after. So it's probably going to tell us to like introduce a bunch of no ops between MTC0 instructions and instructions that will read or write memory depending on the state that changed. Since we know the PIF ROM is correct, we're not going to have to worry about that. But we would have to worry about that if we were actually writing code for the system. In any case, we are going to, it says right here, the operation, in both 32 or 64-bit modes. We have, ooh, wait a minute. I'm not sure what this T or T+1 means in this encoding here. But as you can see, this could actually be cycles. If this is a 2-cycle instruction, that would actually make sense. And that also makes these hazards make more sense. That's what I would be guessing this is. Because it looks like in the first cycle, we're going to read the data from the general purpose register. And in the second cycle, we're actually going to set the coprocessor's register with that data. And it's going to be hard to decide if this is just like a 2-cycle instruction or if that's pipeline in some way. I'm not entirely sure. But I think it's actually okay to ignore a lot of those timing details for now and just do all this in one go. And so what we're going to do is we're going to say let data, because that matches the sheet, it's going to be self read general purpose register. And so RT is going to be the index. Oops, as usize. And then that should be all we need to read it. And then we need to actually set the coprocessor register. So that's going to be self.cp0.set register. And then we're going to have the index, so RD, and we'll probably end up making that a usize as well. Actually, maybe not. We'll see. And the actual data. And yeah, so this, I think we actually need to implement both this read method here and also, or function here, and also this set register function on CP0. So let's go ahead and see what the compiler tells us. No method named read reg GPR found. Yep, so that's the first case, is that we need to, down here, I'll put this next to write register, read reg GPR, inmute self, index, usize, and we're going to return a U64. And here we can actually match index. If it's 0, we're always going to return 0. Because if we remember from the different registers on MIPS, register 0 is always, just like a 0 register. And then we do self.reg GPR index otherwise. And the syntax for that is otherwise do this. So that should be reading the register. And yep, so that works. So now no method set reg found for type CP0. So if we go back to CP0, which was down here, we have a function for power on reset, and now we also need a function for write reg. Or yeah, I wrote set reg. I'm going to say write reg. Itself index. I'll just make that a I32 for now. Probably going to want to have that as a usize eventually, but we'll figure that out later. And then the actual data is going to be U64. BAFTech read doesn't need a mutable reference. This current implementation doesn't, so we'll remove that. Although keep in mind that especially with emulators, a lot of this stuff will probably need mutable references later, because especially when you get to like strobe registers, which are registers that like the data you get or set with them doesn't necessarily matter, but the fact that you interacted with those registers in the hardware in some way will matter. So we'll probably have to make that mutable later. But for now, you're right. This will be good enough. Yeah, so CP0 write reg, and this is where I'm gonna just panic right now. unrecognized CP0 register write. And then we'll do the index and data. I think that was the syntax for hex. Yeah, and then because I made it write reg instead of set reg, then that explains that error. Where was this? Here we go, write reg. So we had a U32 for this address, and it complained that I made this I32. I'll just make that U32. And there we go. So now we panicked at unrecognized CP0 write 12 with this value. So if you look at our disassembly, 12 was correct because we did want to write that thing, and then this 872415 232 should match what was in this register. Awesome. So that works. So now we actually are at least executing the right instructions. So we've decoded this correctly, and it is going to the coprocessor 0. Now we actually need to implement what that will actually do. So this might be a bit of a can of worms, but I think we should just actually start to deal with it now. TJS, there is NUTS by Moogly Guy, but that only tests RSP. I guess he's talking about more test ROMs for the N64. And again, I'm going to guess that all that still needs a working PIF to be able to execute. Otherwise, you couldn't get it running on the real hardware unless you replace the PIF, and then you're going to have plenty of other fun issues. The PIF, by the way, which is this is something I've learned from guys I've been talking to. I'm going to search for N64 board. I found a beautiful shot last time. I believe it was this one. This will do anyway. So one of these, because we were looking at these various chips here. This is actually kind of strange to see these coated in metal like this, but I guess that's too. Normally when you have an N64, there's a huge piece of metal shielding over all of this just to dissipate heat. So I guess this is just so that that all makes contact. We were looking at the different chips. This was the CPU. This one was our RCP, our reality coprocessor. So this is handling all of our audio and graphics and all that stuff. Down here was our RAM. Here was a potential RAM expansion, if you ever bought the expansion pack back in the day. And I believe down here is our PIF ROM. There's our PIF chip. And my understanding of this is that it's a peripheral interface, but it also handles a lot of security-related things, including the boot ROM. So it handles the boot ROM. I think it also handles turning the the actual processor on, because I think it actually has 2 boot ROMs, if I remember correctly. Speaking to TJS about this, it has an initial boot ROM that will actually hold the processor off and communicate with a security chip that's in the cartridge. And when that communication has happened and it's been decided that, okay, this is a good cartridge, then it will actually turn the CPU on and start executing the second boot ROM, and that's the PIF ROM that we're actually working with now. So I believe that was the detail there. But in any case, this is that actual chip, if you're curious. So interesting stuff. So now we actually have to look at coprocessor 0. We have to actually look at its registers. So now we're just going to have to start digging through this data sheet again. Here we have CP0 registers. This section here, 5.4. Again, this document was just the VR4300 datasheet. That's another thing that I did since the last stream, is if we go back to the GitHub project, here, I added a bunch of links to stuff. So I added this helpful tools link. As you can see, there's Hexfiend, the online disassembler, and Dash, which is this. Yeah, I went over that last time. But then for literature, the first link here is the VR4300 datasheet, and that's the thing that we're digging through now, and just various other links that I might find. So yeah, so I'll probably start adding to this a little more. Cool stuff. Yeah, so we want to look at register 12. So if we start scrolling down here, whoops. I think I was just scrolling in here. Somewhere in here we should find register 12. Hopefully we actually will in this section of the datasheet. I235, nope. Register 6, 15, config register 16. Kind of interesting that we didn't set that first. I would have expected register 12 to be config. So it actually looks like we missed it. It wasn't in this section of the datasheet at least. Unfortunate. See if I can find a table of registers. Here, status register. So I guess we're setting the status register 12. Interesting. So I want to search for status register. 635 is what this looks like. I mean, this looks like revisions, but 635 is probably where we want to go to find that anyway. So let's go ahead and look at exception processing. 635 status register 12. Okay, so this actually makes a lot of sense why we would set this initially, because this looks like it's under the section for exception processing. Probably going to set some stuff up to allow us to do things without throwing exceptions, or to save ourselves by throwing exceptions when we do something. We'll find out. Status register is a read-write register that contains the operating mode, interrupt enabling, and diagnostic states of the processor. Okay, this looks good. Figure 6.5 shows the status register. Oh, cool. So this is very detailed. Lots of different sections of this. CU controls the usability of the 4 coprocessor unit numbers. So I guess you have to write to here to enable or disable the different coprocessors. CP0 is always usable when in kernel mode, regardless of the setting of this bit. CP2 and 3 are reserved for future expansion. Interesting. RP enables low power operation by reducing the internal clock frequency and the system interface clock frequency to 1/4 speed. Fun stuff. FR enables additional floating point registers. RE, or reverse endian bit, enables reverse of the system endianness in user mode. Diagnostic status field and interrupt mask enables 16-bit addressing in the kernel mode. Here enables 16-bit addressing operations supervisor mode, and here enables 64-bit addressing and operations in user mode. So I guess these here are the bits that we were talking about, the 32 and 64-bit mode. These are the actual bits. I actually searched for these for quite a while yesterday, and it was a bit hard to find, but here they are, so that's cool. And KSU specifies, indicates mode bits, whether super user mode, supervisor mode, or kernel mode. I imagine that that's actually something, well, specifies and indicates probably means you can write and read. So maybe you can do that. I was actually going to say that that's kind of sounds like that's something you couldn't actually write, but I guess you would have to if you wanted to change that somehow. Specifies and indicates error level here. Exception level specifies in case global interrupt enable. So actually probably what we're doing here is at least disabling interrupts. Probably some other things as well. And then we have, yeah, so part of that was this self-diagnostic area. It said here. Oh, jeez. This scrolling thing is getting pretty annoying. Bloop. Yeah, so this here, this DS. And I guess that was here, self-diagnostic stuff. And then various things about the other bits. So I think the best way to move forward with this then, before actually starting on this register, is to first of all map this out, because now we know that 12 is the status register. And then I actually want to look at the individual bits and see what exactly we're setting here. So in Rusty Bicycle, turn on continuous scroll. That's probably will fix that. Oh yeah, much better. Thanks. This. Yeah, so we know that status register is register 12, so let's go ahead and write that. So what we want to do is we want to match on index. And so in the default case, then we're going to still panic like this. So go ahead and put down multiple lines because I hate line wrapping. Actually, just make it say reg there because we didn't know what reg it was in that case. And if it's 12, then we have the status register. So we could actually also, yeah, I do actually want to write status reg. Or did we separate that out? Yeah, reg config we split up into a bunch of stuff. We'll probably do the same thing with the status register. Reg with the data. I think we actually need a scope here for that. Yeah, so we're going to want to actually write the status reg. So the first thing I actually want to do is just print it. Yeah. There's that same number. I would love to be able to print this in binary, and I can't remember exactly how to do that. But actually, you know what we'll do? So we'll grab this, and we'll use our console calculator, and we'll run that as decimal and turn on binary. I guess these have hotkeys too. I haven't actually used this much, but I want to. Oh, it's these. Control 1, 2, 3. Oh, that's so good. Cool. Again, thanks to Daniel Collin for pointing this out to me. That's awesome. Yeah, so let's actually look at these bits. Now, it's probably the case actually that we'll end up writing set methods for all these. That just go ahead and set all these, but like there's probably a lot of this that we won't actually respect what it's setting. So like, I mean, we could ignore a lot of these values and just like say, oh, we'll deal with those later. But I still actually want to do a lot of like the encoding and like getting all the different pieces of data out of this register right now, just while we're at it. Even though what we do with that data will probably come in fix later. If we look at the first 4 bits, yeah, so one of the things that's really subtle here, I hope you guys can, let me see if I can zoom into this data sheet a little bit, because I really want you guys to be able to see this. So here, in the coprocessor enable stuff, or coprocessor usability section, you'll notice the writing here. It says CU3:CU0. What it usually means when you see that colon syntax, and if you've ever worked with a lot of hardware stuff, you'll see this a lot. Particular, I mean, even if you've done like hardware code like Verilog, what that means is that the bits actually go from CU3 to CU0 in this order, like left to right. So when we look at the bits here and we see 0, 0, 1, 1, what this is definitely doing is enabling coprocessor 0 and 1. And my understanding is that coprocessor 1, again, because we're in kernel mode, is always going to be enabled anyway. But I guess we're just setting that bit because we have to set everything else anyway. But then coprocessor 1, if I remember correctly, was the floating point coprocessor. So I guess we're enabling that as well. So these first 4 bits are definitely trying to enable those. Just really quick, I want to look at the other things it's doing. The next bit would be RP, which enables the low power operation. No need to do that in N64. FR is the next one, which enables additional floating point registers. It looks like we're enabling that. Then we got a whole bunch of other zeros. So I guess none of this other stuff we're doing. So that also means we're going to be running in 32-bit mode, which is pretty cool. So now that we know that right away. Move away 000 just gave me the encoding for actually printing this in binary. So I'll go ahead and do that anyway. If you write B here, then you'll get that. And we do. So we get the same representation here. Pretty cool. Thanks. Yeah, so now let's actually start to get at decoding this stuff and actually modeling it. So this is going to get kind of long. What I actually... I'm kind of considering making this register its own struct internally that we can go set data on, just to clean up the code a bit. I think I'll do that. So what I'm actually going to do here is I'm going to take I'm going to make the CPU a different module, and then we'll have, yeah, I'm just going to do some bookkeeping stuff here really quick before I dive into this register, because this file's getting long to scroll through. So if we go to main, so we're already mod CPU, so we're good there. But then we need to make a folder called CPU. We're going to go ahead and stuff this in there. And in here, we need to make a file called mod.rs. And this will say mod CPU again. Might have to make that public, we'll see. And then we'll be able to use this. So then actually everything that uses CPU in here is going to have to refer to it as CPU : CPU. That'll be okay. Let's actually just run this now as is. Let the compiler tell us what to fix. Yep, so the interconnect stuff is the first thing that's going to run into that problem. Oh, whoops, that's actually in CPU. Use super interconnect. This is now super interconnect. Use of undeclared type name CPU in N64. So we'll go ahead and fix that. Yeah, let's go ahead and do that. Module CPU is private. Yep, so we're gonna have to make this a public module here. And there we go. So now it runs again. Bruno Dea, this stream is up for how long now? I think we've been at this for about a half an hour, so not too bad. Oh wait, no, hour and 20 minutes. Yeah, we actually have been at it for that long. We started too. Yeah, so about an hour and a half. Yeah, but I think mostly we've been doing kind of big bookkeeping stuff, so it'll probably be okay. Crazy is saying the bitfield crate might be perfect for this. I'm gonna go ahead and check that out really quick. Pull up what I'm looking at here. So it looks like with this, he linked an example with the bitfield crate, and it looks like you could it looks like this uses a bitfield macro here for the struct IPv4 header, which I'm guessing this is that he's pulling in here. He's doing a bitfield where he's saying for this struct, all these different names of the different values, probably in this order, we'll take all these different numbers of bits. And then source address and desk address. I'm not sure what that encoding means, but I don't think we'll run into issues like that. So actually, let's go ahead and take a look at this, because this is probably really useful if we're going to be decoding a bunch of bits anyway. So this was the Bitfield crate. So it looks like it's not on crates.io. That's okay. We can go ahead and bring that in anyway. Let's go ahead and do that. Cargo TML. I'm probably going to be a little slow to use this because I haven't used this before, but that'll be all right. It's probably faster than me writing all this stuff by hand. Ooh, Ryan Hebert brings up something interesting. Looks like a syntax macro, so it will require nightly. If that's the case, actually, then I'm going to look at that, actually, because if that's the case, then I actually won't use this, because I don't want to only be able to have this run on nightly. But I actually, my gut feeling is that it won't be a syntax macro, but it might be. Where's our macro here? What? I'm a bit confused at where this macro was. We do pull in syntax here, though. Yeah, look at line 2. Feature plugin registrar recipe private quote. So this probably is a syntax macro, and that will mean nightly. Yeah, at the end, it's a compiler plugin. Plugin registrar. So yeah, so my understanding of that is that will require nightly, so I don't think I want to use this. I want to double check that I mentioned somewhere. Okay, still cool to know about, good to look into. Thanks again for the link. So let's go ahead and go back to the cargo file and remove that. And unfortunately, we're gonna have to decode this by hand, but that'll be all right. Shouldn't be terrible. So while I'm splitting all this stuff up, I want to also split up this like control register stuff and also the CP0 in general. And it's gonna seem like we have a lot of like indirection going through these methods, and we kind of might end up doing that, but I think it'll be okay. I think a lot of the function calls will still be able to be squashed. I think the optimizer is going to be able to do a pretty good job on all this. Yeah, so let's go ahead and make that. So we'll do mod CP0. I don't want to make that public because I think only the CPU should have access to that at all. So I'm going to copy all this CP0 stuff into there. Yeah. CP0 to RS. Bloop. That should almost be everything we need to do. Now we should be able to do use super CP0. And now the CP0 here is going to be CP0 colon here. Oops. CP0 is private, and we need to make that public, which is fine. And I think we'll only make that public. And then probably these functions need to be public as well. Compiler will tell me if I made it public and I didn't have to. Yeah, so we're good on there. Yeah, so now what I wanted to do is split out the config reg like we did here, but I'll go ahead and put that in its own file. So I'll actually split this up again, where I'm going to take the CP0 stuff and I'm going to make that its own module. So kill that CP0, move that into there. Oops. Delete the temp file. Yep. And this is going to need mod.rs pub mod cp0. Okay, and then that means our CPU is going to need to do this, cp0, cp0. Yeah, so it builds. And now I want to split up the different registers inside CP0 while we're at this, because I'll close that too. Yeah, because I remember I wanted to open CP0 here, because yeah, we did all this stuff when we were defining stuff for the config register, and I want to put that in its own module. Use super reg config. So we'll do reg config. Yep. And we'll make this public. And that looks good. Yeah, so there's some discussion going on in the chat about is there anything similar to like C or C++'s union that we could potentially use to decode all these bits? So in like an operational perspective, the enums are basically pretty similar. Tagged enums are really similar to that, but there's nothing that's like exactly the same as the really unsafe untagged union. So to my knowledge, it's not something we want to use for this, or something we have available. Yeah, so this, mod.rs, and then mod right config. So that should build again. Power and reset is private on reg config. Yep, that makes sense. So we'll make that public. Not too bad. So what we're going to do now is also go back into mod. We're also going to have mod reg status, and then reg status.rs. We're going to create that file. Cool. Moveaway00 says there is an unsafe where you can transmute memory, and it looks like you can transmute just bit field like this into an enum, but it's unsafe, so I don't want to do that. Gotta be safe. Gotta be Rust. Rusty, rustic. Adverbs. Sorry, adjectives even. Wow. I am scatterbrained today. Okay, so let's actually start breaking down the status register. So here we're just going to model the different bits of it. Yeah, so we know we at least want pub struct reg status, and we're going to have the usability unit numbers. Data Colin, stay safe. That's what we're doing. So I don't want to do just like CU0, even though it's named CU here. Maybe I do want to do that. What did we do for reg config? Oh, also another quick thing I want to do here is like we had reg config and then we called these reg config EP. Let's go ahead and remove those. So I guess we did just use EP and BE in here. Not the prettiest. I might actually want to change that. But at least we can remove the redundancy while we're at it. And actually, I'll remove the redundancy from all these types too, especially because they're private. So there's no real need to call them reg config EP because they only exist in this context. Yep, cool. Oh, that's a bit prettier. Still not very descriptive, but again, we can probably change that. Yeah, I think that's why I put to do better name on all these. I'll add that here. Better names. Crazy says maybe call endiness. I think I want to go over next time we revisit this register, and then when we have the bits up here, then I'll see, because I think this was like big endian mode enabled or something, and I actually wouldn't mind calling it such a long name. But at least for a reg status, we can start with this pattern of just yeah, giving it a much more proper name. Yeah, so this is going to be coprocessor usability. I consider calling it cop usability at coprocessor. Let's just call it the long name. And this will be 0. So we'll have 0, 1, 2, and 3. So these are going to be booleans. Also, let's go ahead and implement. We'll derive debug, and while we're at it, we'll derive default. Because I think, again, if we remember the reset stuff, the only pieces of state that we knew were guaranteed on reset were parts of the control register. And I believe that's why we actually modeled that register earlier on, was so that we can actually encode that. And so I don't think anything in the status register was actually affected by reset. So using default here is actually okay. I'm happy with that. Crazy, why not a bool for? Because I didn't think of it. That is a better suggestion. Array of 4 booleans. Nice. So there's our CU bits. Then we have low power mode, which RP is the dumbest name for this. It's probably for like reduced power is probably what that is. I'm actually gonna mark these CU, just so that if someone comes in here looking later for like the datasheet stuff, then they'll know what that is. Low power enable, call it that. Then we have the FR register. That'll be, yeah. And that I'll call FP floating point. Cool. RE, which is a reverse endian bit. It's so funny to me. Reverse endian. I think we can also remove enable. DS is the diagnostic status field. I'll write a to-do on this. We'll get there in a second. They have the interrupt mask field. Enables external inner coprocessor or software interrupts. So we have mask bits for timer interrupt, different external interrupts. Okay, here's what I want to do. I am interrupt mask. We'll do another struct for that. Same with this DS thing. Status. We'll get to those actual structs in a minute. Compiler will tell me to do that. KX is next. That was 64-bit addressing in kernel mode. So I guess the X is extended, and KS and U are kernel supervisor and user. Yeah, so this will be kernel mode, 64-bit addressing. I think that'll be okay. KX. And actually, for all these, we also so for these bits where it's like 0 maps correctly to like enable or disable, I actually do want to call these enable again. And the reason is that because we're modeling these with bools, then I want like the semantic value true or false to actually make sense in this context. So low power enable true or low power enable false is perfectly readable. The reason why I'm thinking about that is when we get down here for like kernel mode 64-bit addressing, yeah, we can call that enable. Stupidly long name, but at least it's very descriptive. I'm just thinking like if there are cases where there's going to be a bit mask that's more than 1 bit, I'd rather encode that with an enum just to make it more readable. Because we really don't have to worry about like runtime performance with that, with using an enum versus a bool. If we're thinking about that, then something's actually wrong, and we'll go bug the Rust guys about it. But yeah, if we're gonna use a bool, then we need to like name the field enable or something. Diagnostic status. Yeah. So like here we use a specific struct. Also want to do that. SX was the same. So supervisor mode 64-bit addressing enable. Cool. And I'll just copy this for the next one, which is the user one, which is UX. That would be user mode. KSU specifies and indicates mode bits. Yeah, so like this is actually like the perfect example of what I was just talking about, where we're going to use an enum for this. So we'll call this mode. And I guess that's why it's called KSU, kernel supervisor user. URL is error level. Error level enabled. EXL is exception level. Move away says the fact that it's bool tells us true is enable or yes, doesn't see any extra form in enable. Maybe I'll remove those, but I'm going to keep them around for now. IE is global interrupt enable. So interrupts enable. So I was right about that as well. I mentioned that we're probably, with this instruction in the PI from, we're probably disabling interrupts. And it looked like in that value that we're writing to there that we are. bloop, that last bit there. So it's probably typical for the first instruction here to just write like a constant value into this register. But I'm guessing that further modifications to this register are probably going to be done by doing like read, modify, write, just to preserve most of the bits you don't care about. Yeah, when I think more about enable, just because of the sheer length of these names, I might remove enable there. Yeah, I'll do that. Okay, and except for this one. I'll actually call this enable interrupts. Or actually, no. There are two things that are difficult in computer science, and those are cache invalidation and naming things. And if someone can remember who that quote is from, I would love to share that, because that's one of my favorite quotes. Yeah, so that handles actually writing out what these different bits are. And we'll get to actually encoding and decoding those in a second too. We'll only deal with decoding first, then we'll do encoding if someone does a read on this register. And everyone says end off by 1 errors. Literally 3 people said that. Another one of my friends also said crippling existentialism. Shout outs to him for that. Yeah, so these were the diagnostic status. DTYDE. Let's DTTYDE. This user in the chat says, so timing seems to be a problem also. I'm not sure what you're referring to actually. So we're going to make diagnostic status, and this is just going to be a different struct. I'm going to derive debugging default while we're at it. Instruction trace support. I think that's going to be a bool. BEV controls the location of TLBMS and general purpose exception vectors. That's kind of interesting. Definitely making an enum for that. Location of TLBMS and general purpose exception vectors. Exception vector location. TLB general exception vector location. Yeah, I'll worry about that in a second too. Lots of big names. If it's not going to conflict with anything else, I'll rename that to exception vector location. But since I haven't read that far, I won't do that yet. Indicates TLB shutdown has occurred, read only. Used to avoid damage to the TLB if more than one TLB entry matches a single virtual address. After TLB shutdown, the processor must be reset to restart. TLB shutdown can occur even when TLB entry, which has the virtual address as matched, is set to be invalid. Interesting. Not sure what TLB shutdown is yet, but we'll get there. So we'll call this TLB shutdown. Cool. SR is the soft reset or NMI has occurred. Yeah, okay. Soft reset or NMI occurred. Cool. CH, which is the CP0 condition bit. Condition bit. Strange. TLB to EVL says crazy. That'll be a shorter name. Yeah. CE and DE are two different bits. These bits are defined to maintain compatibility. So we're actually not going to model those because they're to maintain compatibility with the 4200 and is not used by the hardware of the 4300. So they're essentially undefined. So we're not going to worry about that. Yeah. Okay, so let's do this TLB general exception vector location. I think you actually have issues if you derive default on enum, but I'll let the compiler tell me that. I guess normal and bootstrap were the values. I have no idea how these values are going to be interpreted later, but at least we can encode them. And I'll add a note on there for better name as well. Yep. Another thing is that I know I'm like defining like the prerequisite types before the higher order types that use those. I'm probably actually going to start reversing that because I find it so much more readable if you can like when I go into the regconfig.rust file, I expect to see this struct, and then I see these other things which makes me look deeper, right? So I'm like reading from like top down reading, if that makes sense. That's gonna be a bit better. Crazy says, also shouldn't it be called TLB general? Pretty sure the compiler will complain about that. I'm not quite sure I understand what you're saying. I'm not sure what the compiler would complain about. BefTech will be out for today. It's nearly 1 a.m. here and I'm really tired. Yep, see ya. Thanks for joining us. Yeah, again, sorry guys in Europe or other places. Like I know it's pretty late. That's why I also at least try to do it in the afternoon. Maybe I'll be able to get myself actually out of bed at a decent time next Saturday and try to do this. I do want to start doing this more regularly on Saturdays at least, just so that you guys can at least catch some of it. A little more convenient for everyone. Crazy was talking about the casing. Oh, he was saying that the compiler might complain that I wrote TLB in all caps here. And he's saying that the LMB should have been lowercase. It may complain about that. I hope it doesn't because this is an acronym, so I'd rather have that capitalized if I'm going to have any of it capitalized. So we'll see what it says. 2000, 10:30 a.m. in Australia. You guys are way in the future. So actually, this is a pretty convenient time for a lot of people, I guess. Or at least the most convenient time for a lot of people that I can probably do if I'm in this time zone. Actually, by the way, in a couple weeks, I'll be in Norway for a couple weeks, and I'll continue to stream from there. So I'll probably have to shift the time again, figure that out. But I'll let everyone know again via Twitter, like I usually do, about when that'll happen. It's just my time zones will say, what is it, CET instead of PST. Well, where was I? Yeah, so I was going to actually move this, actually all this. Well done here. Uvoy00 says the stream is freezing. Sorry about that, but at least my OBS is saying that I haven't dropped any frames. So don't think there's anything I can do about that. Yeah, so I like this top-down way to write this better. Right, so the thing the compiler complained about is default cannot be derived for enums, only structs. Fine. I believe we ran into that down here with this. So whoops. All we need to do to fix that is just remove default on this struct and implement it ourselves. Not a problem. So that's going to be implement the default trait for this guy. And that's going to be function defaults with no arguments. We'll return this guy. And it's going to be this, and we'll just do normal. Kittens, I missed so much. Yeah, sorry about that. Yeah, I don't want to spend a lot of time actually going over what we did. But basically, we're actually only on the second instruction of the ROM. So in the last one, we're looking at this ROM, and we got this first instruction to execute. We're now looking at this second one. MTC0 is move a value into coprocessor 0's register. So what we're doing is we're loading the value that was in T1 set by this instruction into register 12 of coprocessor 0, which happens to be its control register. And all we're doing now is modeling that register so we can actually do that second instruction. So hopefully that catches you up. Yeah, and then now it's complaining that we didn't actually make the interrupt or mode types yet, which is correct. So we do that next. Interrupt mask and mode. Yes, they're going to be under this. Interrupt mask and mode. So let's get interrupt mask first. Where did we find that? Okay, yeah, this looks like it's going to be pretty easy. So we'll go ahead and make derive debug defaults. Struct interrupt mask. So we have a mask bit for the timer interrupt. I think because it's named mask, we'll be okay to just call this bool. Be clear enough. And I'll mark this IM7. Actually, up here, I want to write 7:0, just to make it totally match the datasheet. Someone comes in here looking at this later, they're gonna know where to look. Now we've got IM 6 through 2. So this is mask bits for external interrupts 4 through 0, or external write requests. The reason I'm like about it is because the indexing won't match up with the exact bits we have here. So I'll probably, for the interrupt mask, probably do additional decoding in here instead of making it instead of writing these directly. But I'll model those as an array. I think that'll be okay. So yeah. Write requests. And so that will be, I believe that's 5 bools, because when you get this notation, these numbers are inclusive. IM10. These are the software interrupts. And IP10, the cause register. Interesting. I guess we'll find out what that is. Cause reg. And so that's going to be 2 booleans as well. Yep, and then we have mode that we haven't done yet, which is true. And for the mode, where was that? What did I use for mode? KSU. Yeah, that makes sense. That was this one. Indicates mode bits. So here, what's interesting about this, we're going to derive the bug. We're going to have to do as an enum, so we're going to implement default. So what's interesting about this is we have 3 valid combination of bits. So we have kernel, we had supervisor, and I'm writing these. I'll write the bits here for now. Later, I'll in the encoding and decoding, I'll probably actually remove these because it'll be redundant. But you'll notice that this bit mask was 2 bits, and out of these 3 combinations, there's actually an invalid combination. Because as far as I know, you cannot be in both supervisor and user mode at the same time. So I'd like to be able to model that. Yeah, so that'll be mode. And then that should, yeah, so now we don't have default on here, which is good. Oh, so cool when the compiler just tells you all this stuff. I totally forgot about that. So pretty cool. Crazy, shouldn't you just panic then? Yeah, we'll probably panic when you do the decoding. Write a little note for me. Another thing about panicking there is, depending on how we actually want to handle those errors, we might actually want to do something other than panicking. But for now, panic will be okay. When you're handling a lot of errors like this in Rust, panic is generally something that I don't like to use. It's nice because it's convenient, but it does kill the current thread. Like, it's not like exceptions where you can catch it. Panic will take down your thread. So it's not the best thing to use for errors. But in the case of an emulator, especially one like this that has to be pretty performance critical, returning like result types and those kind of things that Rust would kind of want you to do might actually incur a performance penalty at the frequency at which we'll be doing this. In the case of Daniel Collin, maybe use bitflags macro for mode. I actually don't think I want to do that because of this invalid one. And actually now if we're going to panic on decode, I think I want to keep it as these first 3 and then panic on that last one. And then keep it as this. But yeah, so in general, I don't like to panic, but in this case, it's probably actually going to be our best choice. Because otherwise, like, even for this one case where, we might be able to bubble that error up, panicking would probably be appropriate, because in the same way that you would bubble errors up, you would also have to bubble okay states up all the time. And so a lot of our signatures would be, like a lot of our really performance critical CPU functions are going to end up returning, status results. And I think that's going to end up being pretty heavy. Crazy's saying, well, yeah, how do you recover from being in unspecified mode? Like, he's also like giving another argument for why you might panic there, because it would kind of be unrecoverable, but at the same time, it's like, hey, you know, we could, from the entire emulator's perspective, we could say like, you know, you did this wrong, and then, you know, we freeze emulation, but we don't have to take down the whole process. So like, it's unrecoverable in the sense that like that emulation instances, that's going down. We can't really move on past that in the code unless we ignored it, I guess. But like, yeah, not a good idea. But I mean, we could do better error handling at a higher level than that. But again, I think that panicking is going to be okay. Yeah, we'll probably end up, you know, wrapping the emulator in its own thread and panic from there. We can catch that. Anyway, I'm just thinking way too far ahead. Kittens, I find it a bit entertaining that Russ uses panic. It's like the poor thing has horrible anxiety disorder. I mean, the same thing with like kernel panic. I really like that. You know, Colin, would it be possible to dump some state and then panic? That's true. Later on, of course. Yeah. So yeah, we're gonna impl default for mode. By the way, the reason the compiler knew to do this is because it was trying to write a default implementation for the higher order type, and it found that it couldn't actually do that here because it found this enum was part of the data structure it was trying to implement default for. So it's just telling me I can't do that. Pretty nice. So yeah, we're just gonna return kernel. Oops, function defaults return mode, and then it's gonna be mode kernel. And this should build it. Cool, but we're not actually running anything still because we still got our status reg right. So let's go ahead and go into, I believe it was CPU here was where we did the reg right, or maybe that was in CP0. Yeah, it was here. So what we're going to do is, first of all, reg status, reg status, reg status. And then that'll be self.reg status.write, and we just give it the data. Pretty cool stuff. Just to double check, I want to see how big this was. Yes, this register was actually 31 bits wide, or 32 bits wide. So what I'm actually going to do is do that cast here as U32. Keep the types nice. So now we'll go ahead and go into our status reg. And we're going to implement a function called write on here, reg status. Oh, that was the file we had open above. Well, ooh, Daniel Collins linking that this is coming up later for Rust, custom panic handlers in stdlib. That's interesting. I want to take a look at that. I want to be distracted for a little bit. I'm going to have to look at this later. But I'm really interested in this. So I'll actually bookmark that. Just flash my bookmarks. I think that'll be okay. Whoops. That was a chat. Nailed it. I think we'll be okay with that as well. There we go. Actually, I'm gonna close some windows really quick. Yeah, I just had to close all my chat windows and stuff. Yeah, it should be good. Kittens, I would want to stream, but I always have so many chat windows open. Scared of giving away tons of personal info. Yeah, I'm usually pretty good about closing them all before I start doing this, but just forgot Slack this time, so I had to close that. Yeah, so reg status. So we were implementing pub function writes. That's what it was. Data u32. There we go. And this also needs mutable self-reference. And there we go. So let's go ahead and decode this. And I think I'll also do this for these as well. That'll be nice. Yeah. Okay, so ability 0 is this will be annoying. We'll do data and we'll do a whole bit mask. 0 be 32 bits, not 0. I think it's the way to go. And we're going to do that for all these bits. And again, I believe, actually because the indexing here, that this was 3, 2, 1, and 0. Actually, going down the line, this way is not terrible. But I definitely did not add enough bits here. I was thinking of hex numbers, where that would have been enough. I might actually use hex numbers for this, just to make this not super long. I don't think it's going to be that bad. Might be, though. Pretty bad at doing these conversions in my head. So I guess we can pull up our console calculator again. We can do whoops, hex. No, this in binary. And that's going to be 8 in hex, of course. Yeah, of course. It's 8, 4, 2, 1. So those are those. Then we have you can also do 1 shift left 1 in console calc. 1 shift left 31. Nice. That's pretty good. Cool. I can also do all the like shift right 31 and then and with 1 instead, but I just want to do the bit masks. And then this was going to be RP, so this was low power. And if we're 2, 1, and then we're going to have 8 here. I think I'm also going to try and align these. Self dot. I'm actually going to just do this. Equals. And we're going to do another one of these. Four. And yep. And then reverse ending is the next one. It's going to be 2. It's going to have 1 here. Oh, this was not the worst. Except we just got to the diagnostic status bits. So we're actually going to want to decode like all those, I think. Right, and I think Chris saying maybe do the one shift left 31 instead. Looks horrible. I'll give it a shot. There's one shift left 31 here. Yeah, that was better. I'm gonna have to do a bit mask in a second though. Later. That'll be all right. That'll be okay. Yeah, because here, what I'll probably do is I'll probably set these ones that need extra writes in like a separate column. Yeah, because the status write, or sorry, the diagnostic status is going to be bits 16 through 24 inclusive. So what I think I'm going to do is data shift right 16 and 9 bits. That'll be all right. Ciderol, your keyboard sounds amazing. Thanks. I think these are Terry Reds. This is a Corsair Gaming K95, is it? The one that you pay too much for and you get all the fancy lights, but you don't get all the fancy lights on OS X. Actually, this is another thing I kind of want to talk about, is that I actually want to start streaming other projects as well. And a lot of the kind of projects that I have going right now are like, oh, I'm reverse engineering this USB protocol to make a driver. And I'm going to look into seeing if I can actually stream a lot of that. My understanding is that I totally can. So unless we run into any cryptographic stuff, then I'll have to stop. But might be fun to reverse engineer this one and try and get fancy lights on there. XSKE, pull a keycap off, see what switch it is. Yeah, I'll do that later. I don't want to do that on the stream. Yeah, so we'll worry about that actual implementation later. Now we'll do the other stuff. Self-reverse ending. Yeah, so now we're on interrupt mask. So I guess that'll be another right here. That'll be, the interrupt mask is shift right 8 and 8 bits. I know I can do hex FF there, but that'll be okay. Better to keep that consistent. I'll align these two. Looks nice. So actually we'll do blocks like this, keep these in order. Self dot KX was the next one. Yeah, the kernel mode one. And I'll not do the alignment until we actually get to the next one. KX was the 7th bit on shift left 7. It's not 0. Yeah, Daniel Collins says reverse engineering is legal in most countries, so it should be fine. The there are some copyright issues with reverse engineering stuff that's protected by cryptography, as far as I understand. So do have to worry about some of that stuff, but also XSKE posts a link about reverse engineering that exact protocol. Well, that's the case 70. It's probably gonna be the same though, so I'll have to look at that later. 64-bit interesting. Yeah, so now we have the supervisor mode. I think this is the longest one, so we'll align everything to this. That's gonna be the same thing, except the 6th bit. Move away 00. DMCA is a bitch. It is it is a total bitch, and I'm actually, it's something that actually really upsets me, is that some of the copyright laws are the way that they are in terms of reverse engineering. It's that whole taking away ownership of things that you actually own. Really, really upsets me. So next was KSU, actually. This will be something else. No, because there was the user one. User one. That'll be bit 5. Yep, that lines up for what I'm reading in the datasheet. Cool. And then next we had the KSU. Yeah, so now we have the mode. And here I'll actually do a match. We'll match data, and here I'll do a shift right mask here. KSU will be shift right 3 and 0B11, 2 bits. And so now we can actually use the coding here, KSU. So we had 00, which is going to be mode kernel. And 0B01 is supervisor, I believe. Yep. 0B10 was mode user, and everything else will panic. FPGA Nugget, why is there no language with nice bit ops like Verilog? What he's talking about is actually you can literally just like index something and you'll just get those, which is it is actually really nice. Like you can take a value and index it based on its bits and set it with values or read values from it, which of course makes absolute sense in hardware because what that compiles down to is wires. So that's actually pretty cool. Yeah. So like Verilog and those hardware descriptor languages, they have some really great stuff. I mean, they definitely do the trick for actually designing hardware. But they're also like, you really feel their age, and at least from a software engineer's perspective, they feel pretty gritty, but they're cool. If you haven't done any of that kind of stuff, I highly suggest you do that. I just bought this for fun a couple months ago. It's Altera Max 10 FPGA development kit. And I got it just because of the different peripherals it had. Like, it was my first FPGA. And I made like a pattern generator and stuff. I want to actually make a little 8-bit computer on this. So maybe I'll stream some of that too. Fails Out is hosting me. Thank you very much. I think that's the first time that's ever happened. That's pretty cool. FPGA Nugget says that one has an HDMI transmitter. Yes, that is exactly why I bought this, actually. And so actually one of my, here's the HDMI. And the transmitter chip is this little guy here. And So that's actually why I bought this. Little did I know that the example code that comes with this is really tough if you've never done any Verilog before. So I ended up writing a tool from scratch to like a little build tool that I use now, which I also wrote in Rust, so maybe I'll link that. And another thing I did was actually wrote a driver for that transmitter myself, because you basically communicate with it over I2C. So I wrote a little I2C abstraction, and then yeah, wrote a little state machine to drive that. So that's fun. And actually, it's a pain in the ass, because like if you actually have to do state in hardware, you're doing a state machine. It's not like C, where like the thing that you have guaranteed is that you have stuff you're mutating by reads and writes, and you have sequentiality. Whereas in hardware, everything happens at the same time. So you have sequentiality in like the small, where it's like sequentiality is in when a pulse comes in on a wire, which gate does it hit first in like a sequence of gates, but you don't have sequentiality in like the higher level stuff, like on a clock tick. Unless System Verilog has this kind of stuff, or more modern HDLs have that. But anyway, total tangent. Oh, phase out. I thought it was fails out. It's phase out, so that's fail on me. Phase out, F-A-I-Z-O-W. He says he has two I's in his name. I totally misread that. It's a small font over there on my little Mac screen. Okay, anyway, we're going to panic on this processor mode. So we'll just do invalid CP0 KSU bits. We can actually do this. Let KSU bits. We can print it. Or actually, I'll print the whole thing, because if we print that, we'll get like a bunch of extra stuff. So let's go ahead and print the whole register. What was it? What was that to print the binary thing? That was in CPU that we had that. I forgot it already. I have a feeling it's that, but I wanted to double check. Yeah, where did that go? Just where we just wrote that. RWZZZZ says it'd be pretty trivial to build a helper that does U32 into a lot of these like bool arrays with the U32 indexes here. It'd be pretty easy to do conversions, but I also don't think this is that bad. We'll be okay. Because we're almost done with that stuff, and I wanted to print the data. So where were we? Yeah, we're on mode. So then there's ERL, which was the error level. I'll just align it all nice with this. Yeah, that's correct. Shift left 2. And yep, then we'll have the exception level, which was 1. And then we have interrupts enabled 0. Discoloda from an into trace would probably be great for this. Probably. Actually, that'd be a really good thing for like a pull request if you guys want to make that. And I can go over it in the next video. I don't. I'm not actually very familiar with the from and into traits, so I'd have to go learn it, and I kind of don't want to do that on the stream right now, unless there's like a really simple example you guys could show me. So I think that's it for this method. Sorry, function. Now we need to do, yeah, probably tell us what to do next. So it doesn't like line 67 here because of no semicolon here. And failed to resolve reg status. I'm guessing I know why that is. Probably because, oh, I did that. Oh, because I didn't use it. That'll do. Crazy is saying that you could do impl from with type parameter u32 for mode, and then you can do parsing in there. So I'm guessing what that will do, now that he says that and I think about it, Rust from trait. So you convert from. Construct a self via conversion. Oh yeah, I see what you're doing. I see what you're saying. Cool. Okay, so yeah, let's actually do this because this is really easy. Cool, guys. Thanks for the link. We'll do. El Barezi, what happened to Dash? Yeah, you're right. Should look that up in Dash. I'm still not used to using that in my day-to-day, so. But I still do recommend it because it's pretty cool. Actually, I'll do that now, just to be cheeky. From. Oh, so Dash just totally remembered what I searched for last time. That's pretty cool. Yeah, there we go. Yeah, so what we're going to do is we're going to take the mode, and we're going to implement from that. So the way we implement this is we have function from, but this is t, and I believe the syntax there is we write t as u32 here, right? From trait is only for things that can't fail. You can still panic though. Yeah, that'll be okay. Thanks, Crazy. That was Crazy that said that. Yeah, because we'll do this, as far as I know. Oh, I can't actually do from 32. This is crazy. These are like syntactic edge cases in Rust that I just, the kind of stuff you look up every time. At least the kind of stuff I look up every time. So I just realized how funny it looks that from is spelled the way it is. Yeah, so in this case, Moveway00 says you can actually also, if you just in Dash, you can say something like Rust colon. Oh yeah, and then here it goes. You only show stuff from Rust. So thanks for the tip. Awesome. Let's go ahead and look at from again. Although I think because I did a space there, it looked in that. Yeah, there we go. I'm talking about the word from in the English language. Like it just looks like from to me now that I'm actually looking at it. So yeah, So we're matching this syntax really for mode. So then the from method itself is going to take a U32 and return a mode. So we're actually going to get the individual bits from there too. The nice thing is that we'll implement 2 later, I'm guessing, and we can go back directly to those bits. So it'll make it easier when we do read on reg status here. So what we're going to do is we'll actually do the matching here. Then we can do self.mode. Skeleton says, what tool is that you're using to browse the documentation? Daniel Collins says Dash. Yeah, this is Dash. It is commercial, but it's fairly cheap, and it's really good if you get the right documentation packs for it. Really nice documentation browser. We'll do mode from, and then we'll just give it the data. And that's why this looks a bit nicer there. So we'll go ahead and paste that here. Crazy said, by the way, for impls, you can always return self in there. You don't have to specify the mode here anywhere like constructors. So I'm guessing he's saying self here. I could be wrong. Self. Yeah, I'm pretty sure that's a special case when you do impl. That whatever type you specify here becomes self. So yeah, I think that looks pretty nice. I'll probably start doing that. Self here as well. So every time I see that, I'll probably go and do that now. Good habit. I think I'll start switching to. So yeah, so that was from that was mode. Then we have the other ones that we need to implement as well. The diagnostic status and the interrupt mask. So the reason why I'm hesitating, and I know this might be silly, is that I'm actually thinking about speed concerns on part of this, and I'm thinking about like so we could do the same thing where we did from here for mode and assign it here. We could do the same thing on diagnostic status and interrupt mask, and then assign it. So we would get something like this: self dot diagnostic status is diagnostic status from U32 or from data, right? And the reason why I'm kind of like, I'm not necessarily sure I want to do that is because, and same with this whole reg status, is because I feel like the implementation of that means that there's going to be a lot of copies here. At least a naive implementation will actually do a data conversion here and then copy that data into this value here. Although Rust does know where this data is going to live. And if it can optimize the return and assignment here, then it's probably okay. I'm actually going to go for it because I think that'll be okay. I have a feeling the Rust compiler will do that. Daniel Collins says, look at the disassembly later. So we'll probably will. I'm kind of curious about that. Probably do an isolated test on that and just see if it does that. This should be a fairly simple case. And again, so Discoloto says LLVM does, and they're talking about return value optimization. Again, Rust is based on LLVM, so a lot of those benefits you get from LLVM you get in Rust. Absconding, I'm not entirely sure how to say that in the chat, says, do you know what graphics library you'll use? So my gut feeling is that I will either use Daniel Collins Mini FB, Rust Mini FB. That's if I'm going to be doing the rendering in software. but I might end up doing the rendering with like OpenGL, in which case I'll use Tomaka's Glium or GLIUM. So that's what I'm thinking right now, but that might change. It's likely that I'll do an OpenGL renderer, because I think that'll be more fun than writing a rasterizer. Probably less accurate, but you know, we'll figure it out. XSKE says, why not piston? I think that does GL. I'll have to check that out as well. Piston looks really cool. I haven't actually used it for anything or checked it out, but it does look really nice. So I'll have to consider that too. Crazy is hammering that I should be using data into instead of the from thing, because I can backwards infer the type, so it'll just look a little bit more interesting. So I just want to look at that. So what he's saying is you can do data.into here, and it will just infer the type and use, I guess, modes implementation of into, or I guess that would have to be, we would have to implement into for U32. I'm guessing we don't get that automatically. Also, data in here wasn't data because I renamed that to value coming into the scope, so do that. Self is not available here. Yeah, because we did an assignment there. We just need to return this. I'm jumping around a lot, like worrying about all this little formatting stuff, but I'll figure it out. Crazy92 says into is actually automatically implemented from all the from impulse, so good to know. Daniel Collins says BGFX is also getting Rust support. I'll have to check that out too. That looks pretty cool. Discoloda also says GFX-RS/GFX looks interesting. I hadn't actually heard about that either, so I'll have to look at that. I'm actually really interested in especially all these graphics APIs. So keep the links coming, guys. I think that's very interesting. Not just for this project. I'm just personally interested. Yeah, because we didn't write for all the other types. So what we're going to do is go ahead and do data into on all these other ones as well, and then we'll implement from traits for those. So we'll do that same with diagnostic status and interrupt mask. And you could argue that like you would only want these data structures to be concerned with the data that they care, not necessarily the encoding, and that maybe it's better to have only decoded it in the right here, but I think it's actually just fine because I don't know, I just feel like it's okay. XSKE says, what are you going to do for GUI? I don't think GTK nor Qt have a nice Rust binding. I'm not sure yet, is the simple answer. I'm not sure how much GUI I'll get into with this project. And that'll be, because the thing is that I think I'll actually go for like a plugin architecture, especially for things like GUI, when that comes later. But first I'll just do a command line GUI. Or sorry, command line UI, not command line GUI. Just because like a lot of that other stuff is going to be really nice if this emulator becomes like production good enough, and I hope it does, but that'll be a ways out. In that case, we'll need a GUI, but while we're just doing testing and building this ourselves, the command line is perfectly sufficient. No associated item named supervisor found for the type reg status mode in the current scope in 131. Not sure why that is, actually. You get the same about kernel. Maybe you can't use self here. Crazy92 says, yeah, self only works for types and function signatures. It's really weird. Okay. Good to know. So now we're getting the from stuff isn't implemented from diagnostic status and the other one, which is fine. So impl from, was that E32 for diagnostic status? Crazy92 says, I wonder if there's a good reason for that. Me too. If you find one, please let me know, because I'm also curious. So yeah, so we're going to basically do the same thing for the diagnostic status stuff that we had before. Or actually, we didn't have that before, so good. Diagnostic status 66 for details. And that was these. So this is just going to be more of the same stuff. Self dot instruction trace support is equal to, oops, I forgot the function. Function from value U32 self. Oops, yeah, because we need to return a new one. So diagnostic status. It's so easy to just get really scatterbrained when streaming, I'm finding. Especially when streaming. Way too many things at once for my brain, at least. Yeah, so instruction trace support. It's going to be this. That was the... Oh, hey, this is actually cool. Let me see if these actually did line up. Yeah, that was nice. So in the datasheet here, you'll notice that these indices on the top here, 24 through 16, notice that that wasn't, 0 through 23. That was actually relative to the other bits up there. So that's pretty cool. Gave us the right bits. So we'll do value and 1 shift left 24 is not 0. TLB general, this big old guy. And that will be on a separate line. This dot from value. And I really wanted that to be indented. Emacs doesn't want that to be indented for some reason. Well, we're going to leave it because I don't want to fight that right now. TLB shutdown. Some little things in Rust mode that I want to fix. Little idiosyncrasies like that one. Do we miss one? No, we didn't. We did not. Because there's that 0 bit in there. Yeah, so the shutdown bit is going to be the same as this one. That would be 21. Line it with this. Oops. Soft reset or NMI occurred. Shift left 20, right? SSR. Oops. And then we have the condition bit. What was the condition bit? Was 18. Oh, yep. This should be into here. Thanks to Discolota for pointing that out. Into. I literally just learned this stuff, so I'm going to make a lot of those mistakes. Yeah, and then the other ones we weren't actually going to look at because those were just for, yeah, VR 4300 doesn't touch those. So cool. So that should be it for that. Then we had from is implemented for interrupt mask. So let's go ahead and look at that one. Info from U32 for interrupt mask. Function from value U32 returns self, and we're going to return interrupt mask. And here, yeah, this is where we have those out of order bools. It's going to be annoying, but that'll be okay. So we have the. I'll fix the spacing here in a minute. So that was here. And this one was going to be, which bit was that? I believe that's bit 15. Yeah. We have these various ones. There is a lot to writing emulators that is just pretty boring data entry like this. But yeah, so for this, I actually think we can we actually use like, can we populate it with just like an array syntax? I would like to do that. Otherwise we can initialize these to just, otherwise we can do like false 5 and then do something like this, like let red is this. And do it here. But the skeleton says that it should work if we do this. And I hope it does. So we'll do that. These 5 were in order, right? Let's see in a sec. I'll put that there. Just want to make sure I have these correct. 14, whoops, whoa, not 45. 15, 13, 12, 11, 10. Crazy92 gave some awesome insight on why there is from and to traits. Basically what he says is that you can't just implement traits for types that aren't in your same crate. So like I can't just say this, like I can't just say like impl into interrupt mask for U32 because U32 isn't defined in this crate. So what he's saying is that the reason why there's this from trait is so that then you can still get the benefits of using you know, some U32.into a certain type without having to implement this, because instead it goes through this from trait. So this allows you to basically extend this type with this information by actually extending this type instead. So cool, thanks for the insight. Good to know. So yeah, so I think because this was 6 down to 2 and 4 down to 0. So yeah, so that's actually in the right order. No, it's not. Because we're indexing 0 to 4, so. We'll get the bits in the right order if we do this. And then our software interrupts cause reg is going to be similar. So we only need 2 of these. And that'll be and I think these also need to be reversed because it's 1 to 0, so it'll be 9 and 8. So I think that's correct. Looks good to me. 138. Didn't like that I did a semicolon there. It's supposed to be a comma. That's correct. So now we have from U32 is not implemented for TOB general exception vector location. So we'll do that here. Impl from U32 for this guy. So it'll be function from value. Oh, let's do self here. Better on the eyes. U32 and it will return self. And we're going to return one of these. So what we do here is we'll match on value. Disclota said, I wish Rust had better stuff for arrays and iterators. So I could have just basically done some mapping, map and collect for all these. Yeah, that would have been nice. Would have definitely read a lot better. And there's like a lot of potential errors here. Granted, the compiler could sufficiently optimize that as well. That would definitely be a concern. But I would like to assume that it does. We can look at the disassembly later and optimize where we need to. Yeah, so we're going to match the value. I believe this was 1 bit. Actually, where was this? This is the TLB thing. And which one was that? On a diagnostic status, so that was done here. That was called BEV. What's these guys? Yes, this is really easy. So BEV was bit 22. So we're going to have only 2 values here. 0 maps to normal, and 1 map to bootstrap. And then this, because the value here is going to be a U32 after this expression, there's going to be a lot of values other than just 0 and 1 that we didn't check. So we're going to need to do this. But we know that this arm of this match is actually never going to be reached. So we can write unreachable here, which is a macro. That should do it for that type. And I think that actually just worked. So now what we actually want to do. So now, Christopher Walken. Sorry. I think this is actually printing all of our reg status stuff here, which is actually really cool. So we can actually check if this worked. So again, the bits that we had. Yeah, so we actually still have that here. Those were these bits here. So we can actually look at that directly. So the original one before this instruction ran. Oh, we actually ran a couple instructions. Wait a minute, let me look at this, the disassembly. Whoops. There's that scroll bar. Yeah, so we had an LUI and MTC0 and then another LUI, so it looks like we actually ran 3 instructions. But we're interested in what happened after the first one. So here we ran. If we look at the reg status here, you can see that just like everything is false default values as we expect. That's pretty cool. Yep, looks good to me. So then we get this other instruction here. Of course, our PC has changed. And I want to look at reg status. Yeah, because this would have been after the the LUI. So as you can see, this register has changed. So then it's the next one we're actually interested in. If we look at the status here, now we can see stuff actually has started to change. So in our coprocessor usability, we had true, true, false, false, which matches this here because we enabled the lower ones. So this is correct. That's awesome. I think the only extra thing that we did when we broke this apart earlier was the additional FP regs, and that's 1. And that is true, and everything else looks like it's still default values or false. So that's actually awesome. So it looks like we implemented this enough for now. That's pretty good. Kittens, that output looks so good. It looks good both because it worked and also because pretty printing in Rust is not shit. And then, yeah, so after that, it looked like it did another LUI, in this case 393 whatever that value was. That was in hex. This, yeah, 6K hex. Let's go ahead and look at the disassembly again. So that was LUI T1 with the number 6, which makes sense because LUI is loading the upper with immediate 16-bit value. So it's loading the upper half of that value, which is what this is. So that's why it's 6 is just this. And we've loaded the same T1, so that will change this as well, which looks great. And then everything else should be the same. So that's fantastic. And then we got an unrecognized instruction that is the 3529 here, which matches our disassembly. So it looks like we've successfully implemented MTC0. So that's another instruction. That one took a while because it required us to actually model a lot of stuff. But that's okay. And of course, a lot of the different enable and disable bits and stuff that we've implemented here aren't actually going to be being used by the emulator right now. Also remove these because we did that. And I guess we'll get to those as we come to them. But for now, this looks pretty good. So I'm going to go ahead and commit this. And we got to commit some temp files here. Yep. TC0. And I'm going to push that. Wow, we've been at this for 3 hours. Kind of crazy. We'll push that. And I think now is a good time for a little break. So I'm going to take that. I think it is like 17 o'clock now exactly. So I think I'll take a 10-minute break. Or 17:04. So at 17:15 PST, I think I'll come back. We'll take a little break. Discolota, 3 hours and 1 instruction implemented. Kittens, is implementing more instructions going to be smoother sailing from here? I definitely think so. Again, there's going to be ones like these that are going to take a little while, just because in order to implement that one properly, we had to also implement the register that it wrote to. But the next one, ORI, which is going to be OR value with immediate, that one I'm guessing is going to be pretty easy. Same with LW. Some of these look like they're going to be pretty easy, so that's going to be pretty cool. Going to be some branches already. Wow, fun stuff. Oh yeah, so that should be a lot simpler. BB2000, this will only work on 2 CP0 registers though, right? Not sure what you mean. I think it only works on this one register because MTC0. Oh yeah, no, 2 registers. Yeah, now I know what you're saying. It'll only work on the 2 CP0 registers, which is the status and config register. That's what you're talking about. Yeah. So right now, I think we only actually even decoded the config register. So. Or the status register. I don't think it actually writes to the config register right now, so we'll have to do that if we get to that register. Again, all this stuff will happen as we encode instructions that will actually write to those, and we'll just have to deal with it as we come to it. And it's just a lot more motivating to just deal with it as we need to instead of doing it all up front. Let's go to 3 hours and 1 instruction implemented. I think I already said that, but yeah, that's how it takes sometimes. And Rusty Bicycle is telling me to also add the .rs tilde stuff to my gitignore. I'd rather just leave my gitignore as is. JRI1, you're doing great, man. Keep it up. Thanks for the support. XSKE, meanwhile, I'm sitting here implementing all the branch instructions and set instructions for 6502. 6502, I wish had better instruction encoding and decoding. That's actually the annoying part for those processors. Next, MTC0 writes to config, says BB2000. Then we'll get to it on the next one. So I'm just going to take a little break. And actually, took a little time with these comments. So I'll actually come back at 17:20 PSD. Give myself a little 13-minute break. So go ahead and get yourself a glass of water. Be back soon. All right. I feel refreshed. Played just basically Step Mania that entire time, which I love. Anyway, let's get back into this. So where were we? I believe we were about to start implementing this next instruction, this ORI. Actually, quick, I'll read through the chat while I was gone. Yeah, not that much. Taking breaks, what a normie from kittens. Yeah, I know. Sometimes you gotta do it, though. XSKE, I guess you already left, but see ya. Yeah, so the next instruction that I guess we found here was this 3529 E463, which looks like ORI with T1 is both our source and destination, or source and target, I believe it was, and then this immediate value. So now I want to actually look at ORI. I believe in our data sheet, we can just search ORI. Characteristics. We're looking for the instruction. It's going to be in here somewhere, probably near the end. Boom, CPU instructions. Looks like we got it. And I'll zoom out a little. Nope, that wasn't the one. Here's the encoding. Wow, really? Oh, I think I found a bunch of matches in this section. There we go. All right. Let me try window management again. Bump that one right now. Yeah, so ORI is OR with immediate value. As you can see, we have the source and target here, and then the 16-bit immediate. So if we look at this, the one thing that I'm wondering about is how is this immediate value interpreted? Is it just like the lower immediate 16 bits, or sorry, the lower 16 bits of this get ordered this? And if we look at the operation here in 32 and 64-bit mode, it assigns the general purpose register indexed by RT with the source register bits 31 through 16 or bits 63 through 16 in 64-bit mode, and then just a bitwise OR of that with the and then appends that with the immediate value with a bitwise OR with the previous value from GPR, the source register 15 through 0. So the answer is that this is the low 16, or sorry, this immediate value will be interpreted as just a regular 16-bit value. 0 extended to 64 bits for the OR operation. Or at least that's how we'll treat it. So that'll work. So let's go ahead and implement that. Go back to CPU, out in here. And yeah, so let's just stick that here. Actually, stick it up here with ORI. We'll probably start ordering these based on the actual bits. 1101, so that will actually be up here. And we'll start implementing ORI. So what we'll do, the immediate's going to be the same here. So I'm going to move that out here. Looks like our RS. I'll just stick that up here because I know it'll be useful for other instructions too. Instruction shift right 21. Those 5 bits. Crazy92, shouldn't you use constants for the opcodes or an enum? Yeah, I'm thinking that the whole time I'm writing this too. And maybe we'll do that. But I mean, again, we'll have to do like the same amount of writing. It'll just make this look a little nicer. You know what I mean? So I'm not entirely sure how much we'll gain. And right now I'm just kind of being lazy and not wanting to write that enum. Yeah, Kitten says I think he's going to do that later. Yeah. For now, I think this is good enough. Not the prettiest, but definitely not the ugliest either. Yeah, so yeah, that should be it for our actually everything we need for that instruction. So that'll be self.write reg GPR. We'll do the target as usize. And the value that we're actually going to write is this, which is going to be the instruction was a U32, so we'll take immediate as U64, and we'll do this. So we'll I'll do that as a separate line. So let result is going to be write result like this. And then we'll so we'll do self.read reg GPR. And we'll do rs as usize to get that value. And then we'll just simply OR that with the immediate as a U64. Yeah, that should do it. And then the compiler will yell at us for not having implemented the read yet. Or actually, no, because we did that for we totally did that for MTC0. We implemented the read, so that should actually be it. And it looks like it was. I want to actually look at this. So I do remember that this is the number we had before that instruction. It looks like that ran, and we ended up with this. One of the things. Oh yeah, I think we read that in the original one. I was just thinking in my head that like usually when you implement these instructions, you also have to implement all the like status flags and stuff. But yeah, I think this CPU didn't have a PSW, didn't have a status word with all that information, if I remember correctly. So it looks like we ordered it with something. Let's look at what this value was. In our little console calc here, this was decimal, and in hex, that was, what was the other number that we had in here? Or just similar. E463. That looks kind of wrong to me. Well, let's see what the value was. Let's see what this was. Oh yeah, of course, because we loaded it with 6 and then ORed it with E463. I was thinking that we had loaded it with this value for some reason, then ORed it with 6. Like, that's not right. But this definitely was. So that's exactly the value we should get. Great, so that seems to be working properly, which is awesome. So now we've done ORI, so I'll do a quick commit for that. Cool beans. So now we got to MTC0 again, I'm guessing, because it looked like, oops, where are we? Yeah, so that was the value. Because it looked like we panicked on unrecognized CPU reg, which is reg 16, and then the value that it was going to write. By the way, I'm going to make sure that that's written in hex, because that's going to be much nicer for us. That wasn't here. Yeah, we wanted, that'll work for that. Just display the number for the reg, and then I want hex for the value. Much better, so then we can get the actual value that it was trying to write there. And it was trying to write that to register 16. Now I believe, was it BB2000? I believe he said that that was the control register. I'm just gonna double check. I'm like 100% sure he's right. I just want to see it in the datasheet. Yeah, a config register here in 16. I'm probably mixing up when I keep saying control. I mean config. I'm gonna mix those words up a lot probably. Yes, that was the config register, so that's awesome. 16. So we'll do self dot. Yeah, and actually we don't need this method now either, because I think this is really redundant. Unless multiple things are actually going to write to that reg, and I don't think that's going to happen. I think that's just going to look a lot nicer. So we'll do the same thing here, self dot reg config.write data. And actually, because of the order that these come in, I'm going to swap these. I think that'll look a little nicer. Makes my brain happier. Cool. And this will, of course, not run. Oh, yeah, when I moved this, I forgot to move the comma. No probs. Yeah, and oops, we need to do the reg status was as U32. So it only cares about those 32 bits. Crazy92, why is the data parameter U64 instead of U32? It was because I don't know if all the registers in CP0 are going to be 32-bit. So when I made this write reg function, I made it U64 just in case. So it's currently what we have now. It is U32 for both, I think. So I think actually the config register is a lot smaller than that. No, it looks like config register is also 32 bits. So for now, it'll look a little weird because we're doing as U32 casts, but in the future, and we probably have to change this by leaving this U64 for now. I could be wrong because I don't really know that much about MIPS. RWZ, why don't you want to implement from for reg config? Because I hadn't thought about it actually till just now. Totally could do that now that we've done that pattern for reg status. So let's actually go ahead and do that for reg config. Except I think actually at first this will complain now that I don't have that write method, so we'll just add that really quick and add a panic or two to. Then we'll go and do all the rest of the stuff. Yeah. So I know that that's going to be U32. I'm wondering if that parameter was named in here. Was it data? Yeah, data. The reason I'm unsure again about what the size of all the different config registers is I don't think that was actually mentioned anywhere in the datasheet. I think they're all like a lot of arbitrary sizes. Probably U32 is the max though, and if we find that later, we'll change it. For now, we'll just panic here. Or actually, wait a minute, because wait a minute. Yeah, this should run now, no panic there. That's good. Because if we're going to use that from pattern in general, BB2000 says several CP0 registers do have 64 bits and 64-bit mode, so that's good to know. So then we'll leave this as U64, and we'll cast it to U32 here, because these registers only ever deal with 32 bits. So I think that's the appropriate place to do that cast. But yeah, so another thing that's happening here is that this write function here on reg status is also just assigning a bunch of its values, from this value. So we should actually do from on reg status as well, if we're going to use that pattern underneath. And then we'll do the same thing for config, just right off the bat. So let's go ahead and do that really quick then. So actually, this will be from U32 for reg status. And here we'll do, so function from value is U32 self, and then we'll do this. Yeah, so now do self dot with nothing, place all these. We'll do space equals with just colon, place all these. And then we'll do, no, don't go further than that, stop. And then we'll do replace with semicolon, make it a comma. Okay, and that should do it. Crazy, it says just be aware that from makes error handling nearly impossible, so it might not always be the best solution. But right now, as long as we're just going to panic on these errors, I think it's going to be okay. So what that means is that this will actually be self.reg status is data.from, or sorry, data.into. Yeah, so I also need to do a different encoding here. Usability is going to be one of these. I think that's the only one here. Unresolved name data.in data, yeah, because I forgot to rename data. Trait convert from is not implemented for the type reg status. I believe that's exactly what this was. Oh, because it was from U64. So let's cast that. I still think it's more appropriate to cast here instead of doing just switching to U64 here, because semantically this only will ever represent 32 bits. So I think that's more correct. Field diagnostic status is set more than once. I don't know how that happened, but it was correct. Yeah, now it panicked at the same place. But that was a nice little refactoring. And yeah, so I'll do the same thing here too. Okay, and then we can write self here, so I'm just gonna fix that really quick. Yeah, so now let's actually look at that config register. So I believe last time we only dealt with like certain bits in here, and part of me really wants to just do the same thing. We'll see. Yeah, because we only initialized EP and BE, which because of the cold reset stuff. Yeah. Kind of interesting that there's just like guaranteed bits that are going to be here. That's going to be important when we actually read out the register. Yeah, so we did EP and BE. We didn't do any of the other stuff. EC is the operating frequency ratio, which is read only. Yeah, because it says that value is actually set by div mode pins. So I'm actually going to ignore that as well for writing this, because that's for our purposes for the N64, that's going to be a constant. Maybe I'll like dependency inject that later for the whole CPU, but figure that out. So then we have the CU and K0 things left, I think. Oh, also, I want to actually yeah, we can take care of these names now. Let's do that really quick. just going to remove some errors while I do this. Time to do some cleanup. Yep. So we want to write config. That's good. Yeah, EP. What was EP? This is why I'm renaming this. Transfer data pattern. Good thing that was called EP, which made sense. So we'll go ahead and call that transfer data pattern. And for these values, so it was D, and this was it just says D in the datasheet. So I'm actually going to leave that one for now. Not entirely sure what those means. Maybe we'll figure those out later. In the RFU stuff, I believe that's reserved for future use. So let's actually panic when we write that instead of representing it here. Crazy92 says D might be default. I actually have the feeling it has to do with like double word or something. Just because the way that the other one's written in the datasheet. I'm not really sure, so I'm going to leave them until I know better. Ryko Haxor says, or Ryko probably says it means normal data transfer pattern, whereas DXX is for weird buses. So let's actually call that normal. And then I'll leave the other one. Let's do this. D. I'd rather call this data transfer pattern. The transfer data pattern. Because I speak English. Yeah, so the next one was that BE. And that was going to be, yeah, like Indian mode. So we'll call this Indianness. And then we'll encode bigger little. I guess we could, never mind, this will work. This will be good enough for this. That is much more readable. So I think this will still run. Nope, because of this. So this was data transfer pattern normal. This is data transfer pattern. This right here was Ennemis. That'll be Ennemis : big. Fancy. Good. So now when we look at our write config, data transfer pattern is normal, Ennemis is big. That's pretty cool. That works really good. So this was nice to do that little rename. So now we're going to go ahead and implement this correctly. Cryzen 82, endiness is big endian. Not sure what you mean. Oh yeah, that you can just like pull it in, and yeah, I think he's talking about just aliasing that value, so it just looks nicer. Ending is big endian, but this is all right. We're okay. Yeah, so let's actually implement the right here. So again, EC is ignored when we actually do the writes, so I'll ignore that. EP is the data transfer pattern, so we'll go ahead and set that. So we'll return a reg config where the blue tracks. Oh my god, it's Jake Heartface. I don't know who you are. I don't recognize your screen name. But hi, apparently I know you. Data transfer pattern is going to be yeah, it had like these weird values for this. We're gonna do a match on these. Oops. And we'll match. What is this? This would have been value. The EP, so that's 24 through 27. So we'll shift it right. 24, not 42. Rocco Haxer, thanks for saying my name correctly the first time. By the way, most people go for the incorrect Raj pronunciation. Yeah, again, I lived in Norway for a long time, so I'm kind of used to the J being used that way. That's probably the only reason I said it right. Kittens, big endian, and little endian sound cute and fun until you try to learn what they are. Yeah, they're really just annoying. Blue tracks, it's Lars from TT. Oh, like living Lars. Hey, man. Good to see you. Or wait. I believe that's the Lars that I'm thinking about. Good to see you, man. 24 and what was it? 3 bits. Looks like 4, 5, 6, 7 inclusive. So that's gonna be 4 bits. Oh yeah, of course, Aslar. Sorry, I had the right person in my head, but I said the wrong name. Thanks, buddy. Forgot living Lars is the Lars from Bypass Bandits. I forget he does that. Yeah, but yeah, I remember daffodils. There we go. Data transfer pattern. So we're doing that. Yeah. If it's gonna be 0, then we'll get yeah, the default value. So and then if it was 6 for some reason, we get this other value. That makes sense. And then anything else, we're gonna panic. And I'll do EP here. Then we'll print that. And we'll just print the whole value again. So that'll be bloop, bloop, hex. And that'll end up being on the next line. Or will it? It won't. Good. And no semicolon there, because we're just going to return. Yeah, so that looks good. So that's the data transfer pattern. And then the other one was the endianness. And for that, that was the BE region. So that was over here. That's bit 15. Yeah, let's actually also do data.from on these. All right, data.into. So we'll implement the from trait. We'll do it after. Impl default impl from U32 for data transfer pattern. Function from value form U32, and that's going to give us a self. And so this will be, yeah, then we do this. Nice. Yeah, that'll work. And then we'll do the same thing here for endiness. Sorry, this is value.into. Clearly. And so we'll do that here. Go from U32 for endiness. Kittens is fun first, but I gotta go. I'll definitely watch this again on YouTube when it goes up. Thanks for joining us. Crazy pointing out my typo. It was into and not I wrote info. Yeah, so now we get that region. So we'll just match value shift right 15 and 1. And if we get, what was the endiness? Yeah, so 0. 1 was big. And the other one will actually be unreachable. Good, good. Crazy92 says interactive Twitch chat compiler. That's exactly what this is. Nice little extra level of error checking. It's almost like it's integrated in my editor. Yeah, so now, oh, wait a minute. Okay, so actually we got an unrecognized instruction because I haven't modeled the rest of that config register yet. And so it just set these values happily and then moved on, I guess. So that actually needs to be fixed. We need to implement the rest of this. So we had, yeah, it was the CU and then the K0 regions. And then, interestingly enough, oh no, okay, so it was just pointing out these other areas. Just that these other regions return, you know, these bits when they're read. So all we need to do is the CU and K0 regions. CU is actually reserved for future use, but it can be read or written by software. Okay. I'm just going to call that CU then. And we'll just make that like a, make it a U8. Or actually, was that 1 bit? Yeah, we'll make that a bool. And then K0. Iberezi, live code linting. Exactly. Yeah, so K0 sets coherency algorithm of kseg 0. What? Okay, so it's basically if the cache is used or not. So let's call this kseg 0 cache enabled. Make that a bool. And then these should be easy to implement there. Yeah, so we'll do CU. It's going to be just whatever value is at that region, which is the 3rd bit. Value, whoops, value and it's not 0. 1, shift left, 3, that'll do that. And then the kseg 0 cache enabled. For the kseg names, I'm not going to expand that to kernel segment because I think that one's pretty obvious. But I could. But I won't. kseg 0 cache enabled, there were only, it looked like 2. Okay, so it was 0 and 0 and then others. Yeah. So that means the other ones are going to be valid, but they just mean that the cache is used. So here we'll just do match here. Value, whoops, shift right. What was it? Where did that start? Nothing. So it's actually value, just these last bits. And we've got 0, 1, 0. And that was cache is not used actually, and everything else was true. And I wrote that wrong. And that should do it actually. The parts of that register we cared about. Reconfig 30 was here. Oh, whoops. True. There we go. Yeah, so I guess I do actually want to look at that. Why is that a match and just not a Boolean condition? Because I am being ridiculous. There we go. And so yeah, so I want to look at our assembly here. So after this other MTC0, we got an LUI, and then this LW is probably going to be the instruction that we're crashing on here. Yeah, 8D, yeah, that's that one. So if we go back one instruction, that's what this represented, the state after. And then the state before that, yeah, it looks like it said this other reg, which is T0, so that makes sense. The one before that was actually the MTC0. So this state we're looking at here is the CPU state after the control reg was set. So if we look at the control reg here, we're going to get like, sorry, I keep saying control reg again. It's config register. So if we look here, we're going to get default values here. Data transfer pattern was normal, endiness was big, CU was false, and the kseg 0 cache enabled was false. And then if we look at these, we're going to see the same thing as we did before, except the kseg 0 cache was enabled. So now I actually want to look at what value was actually written to that. And I believe that was this value here that we had earlier, 6E463. And my guess, if we look at that in binary, oh no, that was the wrong number in binary. We wanted this number. Yeah, we can just use this, can't we? Cool. Well, I want that in binary. So now I want to look at this bit pattern and see if that actually matched to what we got. So if we go ahead and look at the datasheet again. So we had this bit here, which is going to be 0. The EC whole portion is basically going to be garbage if we're writing this. So that would have been the 30th, 29th, 28th. However, I do want to look at what this would have returned, because it's probably writing a 1/6, which might actually make sense with the clock divider. We'll figure that out later. And then we have the EP bits, which was this 0, 1 here, it looks like. That was the data pattern. Or did I read that wrong? I definitely read that wrong, didn't I? 31, 38, 29, 28. Yeah, so that's part of that actually. 27, 26, 25, 24. 1110. I think I'm totally reading this wrong actually. One, 30, 29, 28. What's the operating frequency? So that was actually 110, 1/4 here. But actually it's here. 1/4 master clock, yeah. And then we have 27, 26, 25, 24 for the EP. Data transfer pattern. This is not the number 6. Or 0. That's a bit strange. I mean, again, I know this is garbage, but like, It's actually strange though that didn't like panic in that case. But can probably ignore that. Let's actually just look at the bits we care about and see if that's just garbage, because it definitely could be. So the other bits we had that we actually cared about was there was the BE segment, so that, or the BE portion of this. That would have been bit 15. Now I see what happened. This is not the full 32-bit value at all. The calculator only shows 26 bits. That's exactly what Crazy is saying now as well. As soon as I started counting back from that, I was like, oh, okay. So these K0 bits, let's start there and work our way left instead of left to right. So this is a coherency algorithm, and again, this was gonna do 0, 1, 0 if the cache was used. Otherwise, the cache was not going to be used. What did we say that kseg cache enabled was true? We found. Was that first bit ignored? 0, 1, 2? That's a bit odd. Oh no, yeah, others cache is used. So if we wrote 0, 1, 1, then the cache would actually be used. So that could make sense. The CU was then set to 0 here. The BE for big endian was probably going to be set to 1. Was there some extra bits in here? Yeah, so then we actually have this weird bit pattern after the CU here, which hopefully matches that actually. 0, 1, 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1. Looks like it was that segment. So that looks like that matched, which is cool. And then we had BE, so if it was 1, it would be big endian, which matches here, what we have. And then we have the other parts, so like the transfer pattern. State transfer pattern, single block write request. Was that next, actually? Or was no, okay, so there were some other bits after that that we need to consider. And again, this is just going to be lots of zeros and then 1, 1, 0. And it looks like that's exactly what we got here, and some zeros in front of that. And then the EP would have been set to regular data transfer pattern in that case, which is what we got, and then the other bits wouldn't have mattered because we can't write to those anyway. So actually, this looks like it was totally correct, which is really cool. Crazy92 corrected his previous comment and me saying that to 28 bits, which is definitely correct, because that's actually a multiple of 4 other than 26. Yeah, so this actually looked like it totally worked, which is really cool. So now we've looks like we've implemented the config register as well. And I actually said it right that time. So I'm not going to say we're completely done with that because I have a feeling we're not, but definitely done with that for now. So I guess we just keep working on instructions. By the way, guys, I think I'm going to go at this for another hour, and then I think I'm going to get myself something to eat. Getting pretty hungry. And then maybe I'll stream later, but I actually probably won't. I think this has been a pretty good day. Yeah, so let's look at this next instruction. Just make sure it matches our disassembly here. So that would have been this other LUI, and you'll notice this loads T0 again, and like I said earlier, and so as you can see, T0 is populated now with what looks to be the right value. Let's go ahead and double check that. So that would have been decimal, and we want to look at that in hex. So this was LUI with A404, which means it would have loaded the upper 16 bits with that value, which is exactly what we're looking at here in T0. So our LUI is still working correctly. And then we've got, this unrecognized instruction here, which is LW. And so I have no idea what this notation means with the 16 around here, but I guess we'll find out. So let's go ahead and look at LW in our data sheet again. Lots of LW. Load word. Aha. So the 16 is probably specifying base, because it looks like here, Crazy says loading from RAM now. 16 is probably the offset from the address in the register, and reads the word from there. Skeleton says, yeah, it looks like it. Is it AT&T syntax? I don't think that's AT&T syntax, but well, maybe that part's related to AT&T syntax when you're actually doing reads like that. But I think, yeah, it looks like that was whatever this base value was here. This looks like that 16 probably encodes this value here. Daniel Collins says, no, it's not. AT&T syntax is horrible. I agree. I mean, I've only ever seen AT&T syntax for x86, and at least against the Intel syntax, it's really, really ugly. Crazy92 says, no, base is the source, so that's the T0. Yeah, but I'm looking at what this 16 in parens means. I'm not sure what that means. Let's just look at the data sheet. Yeah, so offset, that's what it is. Okay. Gotcha, offset base. Okay, yeah, I'm just reading this strangely. Okay, yep, that's exactly what this is showing us. LWRT offset base, so this is exactly the form here. And you guys are totally telling me that same thing in the chat. Blue tracks, unfortunately, I gotta go. I'll talk to you later. See you later, Lars. Ryko Hacksaur says T0 plus 16. I would definitely believe that, actually. That's probably exactly what that is. The value in T0 is going to be used as the base address for the word we're reading, probably, and then there's going to be an offset. Like we're going to read 16 bytes after that. And then we're going to read that into RT, probably. That's probably what this is going to do. So yeah, so if we look at this, we take a virtual address, which is going to be... Yeah, these different bits of the offset. I don't really know why they wrote it. Oh, it's a sign extend. That's what they're writing there. Yeah, 16 bits of the last bit of the offset plus the offset plus the register specified by base. And then we say that the yeah, then we do an address translation on that. And then the yeah, and that'll give us the uncached physical address. And then we're going to actually do a memory load on that. For some reason it says uncached here, which is strange to me. But I guess LW might always be uncached. Maybe that's it. Not really sure. But then we, yeah, so I'm guessing this is just saying that we're going to read an uncached word. Yeah, with all these other physical address and stuff. At the end of that, we're going to store all this in the general purpose register. So I'm guessing that the way we're going to write this is going to end up being a lot simpler than this. I think just the notation is a bit confusing here. But we do actually open ourselves up to exceptions, like a TLB miss, TLB invalid exception, bus error exception, address error exception. So none of this is going to apply in the PIF, I'm guessing, because Rico Hexer is saying just ignore what that's saying. It's what the data could be. Okay, interesting. But yeah, again, on these exceptions, I don't think we're going to hit these from the PLB because, as we saw from our processor status, we're not using the TLB even if we're going through that case x0. And I don't think that these bus error or address error exceptions are going to be triggered by, like the 5th instruction in the boot ROM. So interestingly enough, though, we will need to worry about this here, but I think, or we will need to worry about this later. So I'm going to actually write a note in the instruction to check that, but I think I'm just going to ignore that stuff for now. So anyway, this is load word. Crazy92 is saying maybe there's some kind of LWC for like cache loading. There probably is a different instruction for that. It does look like this is going to be uncached. And my guess too is that what this is actually going to start loading is values from the cartridge ROM. Maybe something else, but I'm guessing it's going to be loading a value from there and not caching it for whatever reason. Then it's going to start doing some weird CRC bit manipulation stuff, because we do know that that's going to happen. Okay, so let's go ahead and implement this. Just kind of keeping the order of the instructions here. 100011. This is going to be LW. Actually, just going to capitalize all these. Fix capitalization on all these. Make them all lowercase. That's how I'm going to write them. Daniel Collins says, what's the address it's going to load from? I guess it's time to look at the memory map. Yeah, we'll be in a sec. I think we've already... because we do actually have some really basic memory mapping stuff already, based on the interconnect. And if it goes anywhere outside this first segment, or if it goes in this first segment, we'll get it right, and otherwise we'll get a panic. And if we get a panic, then we'll look at the memory map, because otherwise we already have that address translation done. So put this on that line again. Also, I kind of just want to clean this up a little bit. Rico Haxter says what this is saying is that it's either the uncached address, physical address, or it's the physical address, V address that gets TLB'd. Oh, I got you now. Yeah, it's doing the address translation to get whether or not it's uncached and the physical address, and then it's going to load memory based on that data. That's what you're saying. Yeah, no, okay. Yeah, I was confused by this notation. This is basically destructuring. Rust has this too, by the way, where you're loading both of these values from this. Correct me if I'm wrong, Rico Haxer, but I'm pretty sure that's what you were trying to tell me. Is that the address translation is going to tell us what the physical address is and whether or not it's cached. And then we're going to use that to actually load the memory. For our purposes, so actually, if we look at all these exceptions, which is TLB miss, TLB invalid exception, bus error exception, address error exception, these are actually all things that are going to happen based on the code we've already written. Because if we just actually write something to go and read a value, and we make sure that that method is going to catch all these exceptions, then this one particular instruction isn't going to have to worry about that, because that's going to be the same for any other instruction that's actually going to hit the bus. So yeah, should be good. So yeah, so let's actually do this. Our T is going to be the same that we're used to. I guess base is, if we look at base, it's actually encoded the same way as RS. If I look at this correctly, yeah, 21. So I'll let base is RS just to make it clear when we write the rest of the instruction, and then let offset is the immediate value. Be cool if we could bind two names to the same value, but this will be all right for now. So yeah, so we're gonna get the virtual address, or actually, so where were we actually reading? Yeah, it was right here in read word. But this is actually going to perform okay, this is funny. So in the description here, what I'm worried about when I'm reading this is like, are we going to read a 16-bit or sorry, 32-bit or 64-bit value? It says here, the contents of the word at memory location specified by the address are loaded in a general purpose register, blah, blah, blah. In 64-bit mode, the loaded word is sign extended to 64 bits, which is kind of funny. I was talking to TJS about this on IRC last night. He was basically making the point that, like, I mean, this was totally built to cost, and the 64-bit mode is just kind of this kind of janky thing where internally probably all the registers are just using 16 bits all the time, but your bus is 32 bits, and like, I don't know, it's kind of like a half and half 32 or 64 bit processor really. But the point is we're only going to be reading a word, which is cool. So it's only 32 bits. Well, that's nice. And again, I think, yeah, it does say it's sign extended in 64-bit mode. I'm guessing it's sign extended all the time, frankly. Because that was another thing that that he mentioned, is that when you actually do the flip that bit to make it go between 32 and 64-bit, if you turn it 64-bit on, basically all of the registers just suddenly get a sign extend. And so what he and I were thinking is that it's probably that the CPU is doing that sign extend all the time, no matter what, whenever it writes the value, and then it's just whether or not you see those extra bits if you're in 32 or 64-bit mode. Ditto Colin, gotta go. See you later. See you later, man. So yeah, so I think we'll do the sign extend. And actually, I want to look at LUI. Oh no, I did that here. Sign extend for upper 32 bits. Cool, I did write that. Yeah. So here, I'll actually write the to do there just because I don't want to write the sign extend. But at least we know that we'll need to do it probably. Another thing that TJS informed me of is that, you know, a lot of these games are just basically using the 32 bits. At least the PIF-ROM is always going to be using just 32-bit mode, so not going to be something we're going to have to worry about right away. Yeah, so let's do this. So we're going to go ahead and actually read the value. So we're going to let for adder be yeah, so it takes the offset and sign extends that, and then that becomes, I'm wondering if that's signed. Well, it would be anyway if we do that addition. Right, because in 64-bit mode, it's actually signed extended to 48 bits. Or it has, yeah, 48-bit sign extension. So it is going to be, what I'm trying to figure out is if that offset should be treated as a signed 16-bit value. Because actually, that's the part that's important to us. If we take immediate and we cast this as I16, yeah, that will, as far as I understand, reinterpret the bits. And then what we can do is we can cast that to a U64 again, and we actually get the sign extend. Or maybe we have to go through I64. This is actually something that I did in my Super Nintendo audio unit emulator a lot, is I had this kind of pattern just to be able to make sure that I got all the right bits where I needed them. Because I'm not entirely sure, like if you just cast an I16 as a U64, that probably won't sign extend. But casting to I16 and then casting that to I64 will probably sign extend, and then the U64 just makes it unsigned. So that's my understanding, and that's why I'm doing a cast like this. If you guys know any better way to do that, please let me know. But as far as I understand, this is a way to do it. So what this actually was is our, I'll call it signed offset. And then we'll call this offset as well, just to be consistent. And so then we've actually done the sign extend already. Oh, well, I'll leave the note around for when we actually write the value. Because this will be really easy to sign extend. Because we can just do the cast through I64 as well. Let's do that here too, actually. Let's just fix this really quick. Yeah. Let value is this. So we're going to take the immediate shift left 16. And for a sign extend like that, that'll be as I32. So we'll interpret it as a signed 32-bit integer. Cast that as I64, and then again as U64. Right? And that will do our sign extend. So I think that's correct. And then we don't need this note because we'll just do it. Let's remove this. And I might also add functions for doing this sign extend too. Just because if that ends up happening like all the time, we'll do that. Yeah, so that's our signed offset. And what we're going to end up doing is we're going to, oops, we don't need this either. Cryzen92 is saying that just doing U64 works. And he gave a link. I guess he just tried it in the Rust playground. Yeah, so that did work. Interesting. I found that a bit strange. But, okay. If it works, it works. So then here, yeah, that'll mean I don't need to do through I64 there or through I64 here. Good to know. Yeah. So then what we're going to do is read word. Right, self.read word. Yep. And then we're going to give it that. We'll do virtual address is going to be self.read. Whoops. Yeah, read reg GPR. And then that'll be the base, yeah. Base as usize. So that'll give us our virtual address plus the signed offset. I'll do the offset first. No, didn't want that to go on the other line. We'll do that. And so then we're going to read word from that virtual adder. And then we're going to sign extend that when we write it. So then we'll do value is as U64. because when we just read word, we'll get a U32, and we need to cast to I32 so that it maintains the sign information when we cast to U64. So then we've got the value, and then we'll do self.write reg GPR, and that will be RT as usize with the value. So that should do it, actually, for that. Just going to read through this a couple more times so I feel better about it. Also, this says mem. I'll just go ahead and write this way. I like to try and match those. Do this too, because that was just like renaming these. Signed offset is going to be offset as I16 as used before. Yep, so that's going to sign extend the offset. Virtual adder is going to take our signed offset should actually be sign extended. And then add the value in the register specified by base. And then we read a word, and that goes through all of our address translation and our cache stuff to get mem. We're going to sign extend that too. And then we write it back to our T's register. Okay, so that looks good to me. Let's see this. Cool, so that appears to have worked, and we get an unrecognized address. So this is actually 0404, interestingly enough. And does that, so that address coming in, is that down here? Because, okay, so here's the thing, is that I print unrecognized virtual address here in CPU. And then I believe in the interconnect, then I print unrecognized address, and that's what we're getting. So I'm going to write physical here, so that's more clear. And yeah, that's actually what our thing says now, unrecognized physical address. So that's cool, so now we know that. So now if we go back and we find our N64 memory map, which is here. Now let's look at where that was. So that was here, right? What was that value again? Oh 040410. Wait. 04040010. Yeah. And that's here. So this says SP registers, and I'm guessing by that they mean the RSP, because the line under it says DP command registers, which is going to be the RDP. So again, that's the signal processor and the display processor. So this is going to be the thing that's handling, you know, like vertex transformations and audio stuff. That's actually really cool. So it's trying to write to the registers for the signal processor. And I'm guessing it's just doing some like initialization and like self-test kind of things. So it looks like we're actually at the point where we're going to be looking at that. So what I'm actually thinking, I was going to go till 7 p.m. I'm thinking now actually, because this touches one of the SP registers, looks like it's going to read it. It's probably like waiting for like a ready status or something. I think what I'll actually do, it's 6:30. I think I'm actually going to stop now, and we're going to dig into the SP a little bit next time, I think. Ryko Hexer is saying the RSP kind of controls the memory, so it's probably initializing that. That could definitely be. I guess we'll find out. But yeah, so I think I'm gonna cut it off now, and then next time we'll get into we'll start doing that. FPGA Nugget is saying stuff that's what it's actually gonna end up doing is it's gonna copy part of the boot ROM into RSP memory and start running from there. I did TJS also filled me in that might happen, so we'll I guess get to that later. But yeah, so to close it off, thanks again, guys, for watching. Before I go, if you guys have any questions or anything, now's the time. I'm also going to commit. So Iberezi says, how are you handling uploading to YouTube and live comments? So I believe I went over that earlier in the stream. I really wanted to record the chat and also have that as part of the video, but I'm actually somewhat worried about that, like being a liability. If someone comes in here and just like, posts a bunch of porn links or like illegal ROM download links, you know what I mean? Just like inappropriate stuff to the chat, then I don't really want that stuff recorded. Or if they say things that like a quote from a book that's copyright protected, you know what I mean? Just stuff like that. So in a way, the chat's kind of a liability. So I'm just trying to, over time, instead just read messages from the chat aloud that are particularly relevant and respond to those that way. So I mean, everything that's in the chat that's like really relevant, I'll try to. That's why I'm reading the chat a lot. Is like I'm trying to incorporate that. That's why. JRRA1 question: what are your intermediate goals, like between here and getting Mario Kart 64 up? So the first goal is getting through the PIF ROM. That's definitely the first goal, and I think there's actually a lot of stuff we have to get through before we get to there, because as the other guys have been saying, if this is going to start copying itself to the RSP, and then the RSP is going to start running it, then we're going to have to start implementing that, and that's going to be some really interesting hardware. So we'll actually get through a lot of stuff before we touch that. Yeah, so that's definitely the first like immediate goal, is just getting through the PIF ROM. What am I thinking of? Because I definitely have others. So like, there's a lot of the RSP that is actually fairly documented, even by like these like sources like this, like from people who reverse engineered it. I haven't found nearly as much information like that from the RDP, and I'll have to dig around for that. Because like what I'm thinking is like it somewhat makes sense to kind of like do the PIF and then everything that touches, and then do like the RSP specifically, and then the RDP specifically, like try to go in order. But like before you ever get a frame on the screen, a lot of those actually like work together a lot of the ways. I know that like audio is gonna be something that I just kind of push away for a long time. But yeah, I think the only goal that I actually know of is just getting through the PIF. Other than that, I think I don't really know yet, and I don't think I will know. Yeah, BF2000, is there going to be a link to the PIF ROM in the README? My understanding is that I'm not. I'm not supposed to be distributing that, so I don't think that that I have legal rights to do that. JR1 says that's a good enough plan to keep going. Good luck, have fun. Thanks. I'm having fun. I absolutely love this stuff. It's actually really cool that we're already getting to the point where we're, gonna actually start touching peripherals. And you know, my experience in writing the other emulators that I've written, it's a lot of back and forth. Like, you don't just do the CPU, you don't just do the peripherals. I mean, I've always done it this way, where it's like I start implementing the CPU, and then like, oh, you need to implement this region of memory, or oh, you need to implement this part of this peripheral. I just think that's how it goes. Do everything on a per need basis. But it looks like that's sort of all the questions. Yeah. So thanks again, guys, for watching. Again, I'll have this up as soon as possible. The code's already pushed, so that's cool. Go check that out. Yeah, and if you like watching this, go ahead and tell your friends. Give me a party. It's going to be pretty fun. So RWZZ says, I'm just going to say Rwuz says, is it possible to capture post-PIF state and make emulator reset to it without shipping PIF? Yeah, so that's actually kind of what I've had in the back of my head for a plan. Like, I kind of want to do that, actually. After we get through the PIF, like, we need to know exactly what it touched and what it did. It's also a really good way for us to actually start, looking at code and finding out what state does it leave the system in. Crazy92 also says you could probably just do your own implementation of the PIF in Rust. Could definitely do that too. Kind of the issue with that, though, that I actually have is that, as far as I know, like, reverse engineering too much about what that's doing. I'm not really sure if I'm able to broadcast a lot of that process. But yeah. Also, the PIF ROM is, as I understand it, slightly different between NTSC and PAL. The one I'm working with is NTSC. So we need to run the PAL one through here too and capture that state. But I actually think that capturing the state of it is probably fine. So that's a usability thing that'd be really nice. Like, if people are actually going to use this emulator, they don't have to also find that ROM. I believe, though, Rustation, which is a Rust PS1 emulator, is also doing it where it's like you need a BIOS. So, and I think what he does is he says also, like, use the BIOS with SHA being this SHA, and that will work. And I can do that. I can say, like, if you have a PIF dump and the SHA is this, then that's the right one. I can probably put that in the README. So yeah, guys, thanks again. I'm gonna upload this to YouTube right away. It'll probably take a few hours because we've been streaming for like 4.5 hours or something. So, yeah. Rico Haxor, for PS1 you need a BIOS because the games actually import and use functions from it, so it's way easier than re-implementing all of them. That makes a lot of sense too. So I guess it's different reasons with why you need them, but it's the same problem with actually, getting a hold of that data and distributing it. But cool info. Yeah, so again, guys, thanks a lot, and see you next time.